And then we have the covariance matrix describing the spread of the distribution. And so we define this matrix that is basically a norm. So to show how it works, we made first a simulation that was the time of lockdown. Was not easy to make consistent robot experiments because the access to the lab was limited. So here we tried three models for the description of human posture control that were also used in controlling robots. And so we used them with a simulated model of the robot. So what we see is that for the three different models, now I don't go in details because we don't have much time for discussing the single control system, but there were three bioinspired systems, and we see that for each of them we get a different frequency response function. That, as you can see, being an empirical transfer function is a complex function. We have gain and phase. And so we can compare this with the one that we observe in humans. And already in this scheme, you can see the human average is the purple one. One thing you can already notice is that the response to the stimulus is larger in humans, I mean, what we observe in humans than what we observe applying the model we got from literature. So, I mean, it's already makes you think, okay, human likeness doesn't mean on an absolute scale overall better rejection. Somehow the human is more relaxed, especially, I mean, here we have a healthy subject to describe the benchmark. So if we try to put, in this schema, try to put a bit of things together, like we have all the red dots that are the human subjects used to define the benchmark. As you can see, the human likeness is on the x-axis, so you have human likeness measure. The smaller it is, the more the trial is close to the average of the human subject. As you can see, there are some dots that are far away from the average. So all the three experiments somehow are included in the distribution of the dots. And here you can also see we put together the measure, but also Mahalanobis distance, so just making the norm of the difference between the average and the the samples. So without considering the dots, without considering the weight. So in this Mahalanobis distance, we give the same weight also to higher frequencies. And one thing we can notice is that, I mean, for example, these bioinspired control have a larger Mahalanobis distance, so we can see that the difference probably is happening at higher frequencies that are not given a larger weight by the input function. So, but still, and we see that not all the controllers have the same human likeness, of course. And here, at least in this simulated experiment, it looked like the simplest one, the independent channel, where we make a feedback, a direct feedback with the weight of each sensory channel, that in this case was the vestibular, there is an IMU, and the proprioceptive, there is the encoder of the robot, and is the one that was more human-like in this measure. Then we managed also to make some robot experiment, because I mean, we got normal access to the lab, luckily. And what we have done, we took humanoid robot, is our custom humanoid robot called Lucy, we used for posture control experiments, and we put it on the moving platform. What we can see here is that, I mean, we didn't try different control system approach, but we tried the same control system adjusting some parameters to see if we can observe something making the robot behave more human or less human. And, for example, what we see is that here this red star is the standard DEC control. We use this biospy control system called the deck, where we are directly compensating external disturbances. And what we have noticed is that if we lower a bit the gain, we get something that is more human-like, or even if we remove the derivative. But if we remove the gain too much, like even lower, then it becomes less human-like. So what we can think here is that, I mean, the standard parameters were taken from a previous work, like as they were, and then I tried to change them to see what changed. The impression is the same of we have seen in simulation, that humans somehow have a lower gain, they are more compliant than the typical control for the robot. So in the human likeness benchmark, you get also a larger gain that you get lowering a bit the gain of the compensation here. So in conclusion, what we see is that the main contribution of this set of this work is the set of data from human experiments that we can use for benchmarking, and then also the proposal of a metric to compare the human experiments with the robot. This is the distribution of frequency response function from the human experiments. Then we tested 3 different control systems, and we have seen that somehow the typical control system are a bit more stiff. They are compensating in a way even better than the typical robot control system. We have also other stimulus profiles that I have not shown here, that were published in other works, and is designed to test transfer behavior, and then we have also a sinusoidal stimulus that is predictable, but can give a description of, I mean, steady-state response to periodic stimulus. And of course, we have this frequency response function that we propose for human likeness. Of course, it's still open to see, as we have seen, the gain, the response of the humans sometimes is often larger than the robot. So it's good on absolute. From an absolute point of view, or does it prove something like, for example, one thing we often claim when proposing human-like control system is that human likeness entails also a better compliance. So this robot is softer in responding to external stimuli, and of course it comes to a cost of not having a perfect compensation. You have a larger gain. And it can also have some implication in energy consumption, like because if you are applying lower gains. At the same time, there is the risk that if you are swinging too much in presence of the external disturbances, of course, the robot is less stable and may even consume more because it has to compensate larger error as a result of the more relaxed movement. And so thank you. Here you can see, you have seen this system is, as you've seen yesterday, is available in Genoa for experiment. And in case you are interested in this kind of experiments, we are also open for collaboration using our robots and our platform in Freiburg. So I think, you see, I have more than 15 minutes, so I've been fast. We have time for questions. Thank you.
I think we should still take the time for 1 or 2 questions. Any questions from the auditorium?
So thanks, Vittorio, for the presentation, also for helping to install the device and the innovation. I have a question about the stimulus, actually, and how this can be, let's say, tuned in case that you need to perform experiments with robots or humans, maybe a child and an adult that is much different size. So in order to get eventually a performance indicator or metrics that is actually kind of normalized. So do you expect that you use the same stimulus, for example, to test a child that is maybe weighs 10 kilograms and is 1 meter height, and with an adult person, and the same applies, of course, for the robots, the same question?
Well, usually for experiments with humans, where we took this kind of inspiration for these proper robots, there is not a normalization to the height, and everything is usually described in relation to angular sways. So somehow you have the tilt of the platform and you compare a transfer function to the tilt of the body. And somehow we didn't make difference related to between subjects with different height. We take this measure as swing as an input, tilt as an input, and body sway as an output. So it's somehow a sort of normalization by itself. It's all angular. The point is that there is also the possibility to do this experiment with translation, and in that case we are aware that the taller the robot, the bigger is the stimulus given the same movement. And I should say that so far, both in the literature of human experiments and also for what we started to do with the robots, we didn't normalize for the height. It's still an open issue, because I mean the idea is that this approach comes from protocol. We are aware that, of course, if the robot is taller, it can be more difficult to stand that kind of stimulus. Thank you.
Thank you.
Welcome.
Thank you. Any further questions? So let's thank again.
Thank you.
And in order to make up for some time, Leonardo Gysi, we will have the next talk on the project bench towards an objective evaluation of the sit-to-stand motion. I think we've seen this yesterday downstairs, and today we will get the presentation on that. Leonardo.
Good morning, everybody. My name is Giacomo Severini. I'm presenting on behalf of Leonardo Gysi, who's not able to come today. And I'm talking about our project bench. That was a project coordinated by University of Stuttgart by Leonardo Gysi in collaboration with me at University College Dublin and Dr. Cristiano De Marchis at Roma Tre University. So the aim of bench was that of developing an instrumented chair for objective evaluation of sit-to-stand, and with application on both human studies, studies of interaction of human with exoskeletons, and the humanoid robots. So as we all know, sit-to-stand is an extremely common test that is used for assessing dynamic balance and lower limb coordination and strength. And it has significant clinical relevance. It's used as, it correlates with independence, the outcome of rehabilitation, and it's a predictor of the risk of falls in both impaired population and elderlies. Traditionally, sit-to-stand is performed with just a chair and a timer, a chronometer. Although in the past few years, several studies have been developed with the use, of course, of Vicon or IMU-based analysis of sit-to-stand. As you all know, the validity is somehow questionable because of confounding factors like the personal strategies that people use to do the sit-to-stand and things like that. So having even more information about the task is extremely important. So the quantitative evaluation is also extremely important for the development of control strategies for humanoids robots and for control strategies of exoskeletons when they interact with humans during this particular task, both in assistive environments and in training environments. So in general, there is no standard for benchmarking sit-to-stand, both for humans, humans with exoskeletons and humanoids. So for this reason, we built our chair. So as you can see, it's a very simple system. It's made by an infrastructure that is made of PA6 nylon that is non-conductive and amagnetic. It's completely adjustable, both the height of the chair, the height of the back, and the handrails. It is modular, so components can be removed, replaced, and all the instruments are based on commercially available and newly designed and commercially available components. It is designed to be a system that can be operated by a single operator, so to be as simple as possible. It is detached from the test subjects, so there are no cables attached between the system and the test subjects, and is fully integrated in the EUROBENCH facility. In terms of instrumentation, the core of the instrumentation of bench is two force plates with 6 degrees of freedom, so forces and torques, and that are synchronized with IMU sensors, and it can be synchronized with EMG sensors and mocap system. So this is an example of how the chair is used. This is in the lab in Rome. And this is a test that is the 30 seconds sit-to stand in which a person needs to do as many sit-to stand as possible in 30 seconds. So as you can see also the electrical part is extremely simple. So you get the signals from the two force platforms. Everything is synchronized together with, in this particular case, the data that we get from the accelerometers. Then the data of the accelerometers and the force platforms are used to estimate the kinematics and the dynamics of the task, and everything is sent through ROS to the main, the master computer in the EUROBENCH facility. And so we have a slave computer where all the data are recorded, and then they're sent through ROS to the master computer, where an octave routine is used for pre-processing and calculation of a number of metrics that can be applied to both to healthy subjects, actually to human subjects, human plus exoskeleton and humanoid robots. So the metrics that we developed for this particular test are the following. So there are normally two tests that are done for sit-to-stand. One is the 5 sit-to-stands, so a person is asked to do 5 repetitions of the movements as fast as possible, and the other one is the 30-second sit-to-stand, in which a person is asked to do as many sit-to-stand motions as possible in 30 seconds. So the performance indicators that we derived from these tests are, of course, the duration of the 5 sit-to-stands, where the lower the better, of course, the number of repetitions that are obtained, that a person, the user is able to do in the 30-second sit-to-stands. Of course, the higher number, the better. The duration of the different subphases of sit-to-stand, because sit-to-stand has been classified as different subphases in a series of seminal studies in the past 15 years, like, for example, the moment transfer between when the person is starting to lift from the chair, the extension phase, and then the stabilization phase are the most important. So here, with our PIs in our code, we calculate the duration of each single phase. Then the COP stability, so the average distance traveled by the COP, of course, the lower the better. It means that the person is able to achieve the movement with minimal movement of the center of pressure. The time for unidirectional load transfer, so that means the time that it takes to the person, to the user, to move from the chair to the ground, basically. So to move their load from the chair to the ground. The load transfer overshoot, that means how much the person leans forward mostly when performing the movement. Kinematic repeatability, that means how consistent are the kinematics of the movement through the different repetitions of the task, and the total mechanical power, that is just the power performed by the center of mass. So we didn't have the chance to test this with humanoid robots or with exoskeletons, so we developed a data set with human subjects, but it's going to be available for the facility, should have been. Sorry, Diego, but it's coming soon. And that ideally could be used as benchmarking tool for the performance of sit-to-stand of healthy individuals. So the data set, it consists of the kinematics, kinetics, and EMGs of 13 healthy subjects. So we have mocap data, accelerometers, unilateral EMGs, and of course the data of the force plates. We have available the raw data, the process data, and the performance indicator that I have shown you. So just to show you very quickly the power of this data set. I'll show you two examples of of two works that we are currently doing with this data set, and that potentially can inspire further works with the use of exoskeletons and humanoid robots. So in the first one, since we have most likely the most complete data set on Sit2Stand in terms of kind of data available, we say, okay, let's dissect this data as much as possible. So the first thing we did is a neuromechanical, so we are currently running a neuromechanical study just to see, to try to characterize as much as possible the task. So we started with some very simple analysis like muscle synergies. We found something extremely interesting, that half of the subject are better reconstructed by 2 synergies, the other half by 3 synergies. And in this case, you can see here the 2 groups, when we force the reconstruction of both groups with 3 synergies, you can clearly see that there are 2 different strategies. So we're now trying to analyze, so there are two clearly different neuromuscular strategies that from a biomechanical point of view in reality correlate with a different way to control the center of pressure, both mediolaterally and in the anteroposterior direction. So at the moment, we are finalizing this analysis, and I hope that we can present a paper on this soon. So just to show that having a lot of data on a very simple task can allow you to perhaps get a little bit more information on how the task is performed by people. And as I told before, Sit2Stand tend to have some confounding factors related to the strategies that people use to do Sit2Stand. So we have found 2 particular strategies in healthy individuals that were not giving particular instructions. So, possibly this may help also in the clinical setting. Then a second study that we're currently running in my lab in Dublin is on predictive simulation of Sit2Stand. So we're using the data to validate some, a predictive simulation of Sit2Stand that is based on a reflex-based neural controller. So we develop a neural controller that generates muscular activation applied to an OpenSim model as fake reflexes depending on the velocity and acceleration of the torso. And the optimization is standard covariant matrix adaptation, but it's a very common way to do this kind of optimization using a cost function that maximizes balance maintenance and some phase-dependent biomechanical features. So it's not, for what is the shape of the cost function, this is not really a reflex controller. So it's, an architecture is a reflex controller, but the items of the cost function try to take into account some of the volitional part of the movement. So the idea behind this study is try to see if we can develop faithful reproduction of the way in which Sit2Stand is achieved by people, so that we can pre-test, for example, the effect of adding loads or adding particular forces at the joints, like, for example, the effect of an exoskeleton on the control of Sit2Stand. The preliminary results, so this is an example of the simulation, and the preliminary results are encouraging. So we found biomechanics that are physiological, they're not perfect. And also in terms of muscular activation, they're not too bad. So we see good activation for the vastus, the biceps, and the gluteus. We have some problems with the tibialis, the rectus, and the soleus is not too bad. There are limitations that depend mostly on the fact that we're using a very simple biomechanical model that has a big problem that we should have addressed before, that has the torso and the hip as a single structures instead of having a joint. But that's very encouraging results that inspire us to play with more complex models and use this solution to try different loading condition and exoskeleton support. It's interesting, in my opinion, also because as, a model like this one could be used as an inspiration to develop a control system for humanoid robots, of course, okay, taking into account the sometimes simpler activation profiles of the joints torque that you get from the humanoid robots with respect to the heel muscle models that you have in biomechanical models. So that's it, and if you have questions, I'm happy to reply to your questions.
Yeah, thank you, Leonardo. And I think we have time for one or two questions. But first, I would like to make some kind of business proposal. With this share, could it possibly be a way to have tailor-made, made-to-measure shares for persons? Every person is individual, so why do we have all the same chairs?
Yeah.
Maybe you can found a company to do this. But there could be more serious questions from the auditorium. And maybe just a hint for the technical bench, there will be two virtual presentations coming up, so please make sure that we have everything set up.
Yeah, my question is about this controller. So you use this some muscle activation, no? But you also use the COP, COM also to control the stability of the person during the movement, or not?
So in the predictive simulation, we didn't use the COP, and we used a simpler way to calculate stability, but it could be used. So the problem of this kind of simulations is that the more you make it complex, the more it takes forever to converge, and you may be overfitting. So you try to minimize as much as possible the number of parameters that you use. But yeah, this is something we are considering, to try to use the control of the COP as one of the items of the control function. Interestingly, normally in this kind of simulation, the control function is always has some kind of element on energy minimization. So gate, for example, is extremely important. In this case, if you put energy minimization, the system does not converge, because it's not an energy efficient movement, sit to stand. But COP could be used in this case as dual, as a dual parameter for both, taking into account some kind of energy minimization and balance, the control of the movement.
You should talk with Katia Mombauer, because they are doing very simple stuff.
Yeah. Okay. Any further question?
So. First of all, I see the handles, but the handles were not used, so also not sensorized. So
yeah, the hands can be sensorized, but they're not sensorized in this implementation.
Okay. But so eventually you can also perform trials where you have assistance from the arms potentially to. And okay, my second question is actually that I saw the metrics you use most of the, let's say, of the index you use is about how fast the motion is performed, how dynamic it is, how many times per second, and so on, how long it takes. Also some work on the center of mass. Do you think that will be possible also to use the, let's say, by extracting, even going a bit more lower and estimating maybe the joint effort, to suggest if the postural trajectory of the person is somehow is suffering, for example, from overloading of some of the joints, that they maybe suggest that the actual posture that the person is doing during the sit to stand is not the correct one, and maybe potentially cause injuries or chronic injuries to the person.
Yeah, that's a very good question. So first, for the first part of the question, all the parameters on speed are actually dictated on the way in which sit to stand is evaluated in the clinical setting. That is all based on speed. So for this reason, we try to replicate that. On the second point, of course, that could be, so it's not like we try to minimize the number of PIs, because, but at the same time, we took the PIs on the energy of the center of pressure as something that, should take the redundancy of what you take from the single joints. But of course, you can calculate, the effort of the single joints, and if you're interested in our data set, you have all the raw data and something that actually we are analyzing at the same time. But it's a PI that can be, so these are PIs that can be very, very easily added to the list.
Okay, thank you very much.
You're welcome.
Okay, so sorry, you can see what I can see. Time is up for 5 minutes now. If you have any further questions to Leonardo, please feel free to get in contact with him. And now we will continue with 2 virtual presentations. The first one is by Fabio Bonsignorio, It's HumaBelief, belief space planning for robust humanoid locomotion. Fabio, can you hear us? Can you see us? Are you there? Well, maybe I fill in this gap. I have this aunt. She's about 90 years old. She suffered from a stroke. And in order to recover, she was given the exercise by her physician to do this sit to stand motion.
Sorry, I think there is something not going. Hello?
We can hear you, Fabio.
Okay, because what I saw in your screen was another presentation, but probably a recorded one. I don't know what's going on.
We can see you now, and
okay, I restart. Now I see in your screen my face and the slide. Before I saw someone talking, probably from I don't know if it is a connection problem. Maybe you should check the YouTube channel. I don't know. But anyway, so I'm really sorry of not being there in person. Actually, me and Enrica, Dr. Zereik from the CNR can witness the power of Murphy laws, because we simultaneously had me positive for COVID and the little son of Enrica had a medium to serious accident on Sunday. So that's why we are not with you today. And it's a real pity. This talk is about actually there are two. The first one is about the project that was jointly developed by Aeron Robots and the CNR Institute of Marine Robotics in Genoa, within the activity of our joint lab that actually is from the CNR side, led by Dr. Zereik, who is here. And we'll continue my presentation. We will alternate. I will do the first part of the presentation and Enrica will finish it. So in this small project, what we did was to test. It was an option 1 project, so we did the final test, unfortunately, just a couple of weeks ago at the IIT testing facility in Genoa on the RIMC humanoid. And what we wanted to test was a very well-known hypothesis by neurophysiologist Alain Berthaud made in the 90s, that actually in the humans, the control of locomotion starts from the head and goes down. Actually, we devised a very simple couple of experiments conceptually simple couple of experiments to test this hypothesis. And we decided to try this because actually we did some very good experience with belief space planning approach to control in different areas. Mainly underwater, because CNR INM Institute of Marine Robotics is actually engineering is actually devoted to marine robotics, and also Aeron has a significant interest in that area. But I mean, this approach has proven extremely robust and also very requiring very little tuning. One of the big problems that we all know we have in robotics is many times we have solutions, but those solutions requires the tuning of a significant amount of parameters. Recently, deep learning came somehow to help, but this is a sign that the solutions are sometimes not robust enough. So this BSP was kind of surprise. We had some expectation, but testing it in different environments and settings has proven that it requires very little tuning, and it is quite robust. It's slower than you can see, for example, in the most recent paper that we had on RAM in 2020 with Enrica with an experiment in manipulation on a very, very crappy and difficult to model robot arm. Actually, it is proven robust. Maybe slower than PID but also sometimes MPC, but definitely robust. It is it's a stochastic approach. So it's basically, we definitely have no time to enter into details, but we can find the papers, and also in the paper, in a paper by Zereik, that actually proposed this in simulation many years ago, some 10 years ago. But basically you optimize a number of parameters. And the main idea is that that is probably the reason of the strength of this approach, is that you don't assume that the controller knows the state, but you assume that that you have a belief, the controller has a belief about the state in the term of a Gaussian. So a Gaussian is still not a real word, but it's a good model with respect to assuming a deterministic knowledge with a small error on it. So the main idea is that we work, belief space planning works in the space of the beliefs about the state. And this proves, and then you optimize the steps in such a way that you maximize the probability to be in the right place at the next move, and at any step you act to reduce the uncertainty. So this is extremely attractive as an approach, and you will see that we have used it with great success under this aspect in terms of robustness, now performing the task all the times or almost all the times in such diverse fields like reaching with a very small cheap and poorly engineered, so not well-known model arm manipulator, and in the CADI project for tracking for a robot underwater assistant to keep a fixed distance from a sub operator, an underwater operator. So we were quite optimistic about, so optimistic. We thought that it was an attempt that it was worth to try. And we were actually, I think the results are encouraging, despite the difficulties that we had, that we could only test in the real world at the very end of the project. So now since we have not a big long time, I leave the floor to Enrica, which will talk about the experiment that we performed on both in simulation and on the real RIMC robot at the IIT facility in Genoa. So Enrica.
Thank you, Fabio. Good morning to all. So I'm talking about the experiments. Next, please. Okay. Can you start the video, please? And so after some simulations, we tested our system that Fabio described on the real robot RIMC. You can see here the video. And the task that we required, as Fabio suggested, is simple and consisted in basically tracking a red blob in the 3D space. In particular, the robot was asked to center this blob in its camera image plane, and then to keep a predefined distance from it. You can see from the video that the tracking is continuous. This means that if the blob is moved after being centered for the first time, the robot starts again compensating the error, and so it keeps tracking forever, basically. And you can see that the robot is moving in all directions to compensate this residual error. And if the blob is too close, RIMC is able to go backward. So I don't know if it's still long, but we can see the tracking, and also you can see the velocity and the good performance of this robot. So this was basically one of the first launch of the system. So it worked immediately. And this is not, this is strange, quite strange in robotics, but it happens sometimes. Okay, you can see that he's going backward because the blob is too close. Okay, can you go to the next one, please? Here you can see just a different perspective of a similar task. Note that there is a cable from the top of the head of rim C, and it is from an external webcam. In fact, we had some problems because after the very first test, one of the onboard computer that was the one that was managing all the cameras on board stopped working, and so we could not have visual feedback anymore. So we tried to manage this situation, and we had to replace this rim C camera with a simple webcam. We put it on top of the head of rim C, and all went smoothly, and we were able to continue our tests. And as in this way, we demonstrated also the high flexibility of the overall system. So we were quite happy after being sad because we had this inconvenience, but no worries, no problems. And these tests were all performed using the working controller developed by Robotics. And testing, as you can see, the robot on a flat terrain. Some runs with slopes were also performed in simulation, but they did not have such good performance. So I guess we have to still work on that probably. Next, please. Okay, after this test with the working controller, we wanted to use the whole body controller by Robotics to perform our walking, and using the BSP as a motion planner. This is not so immediate from one controller to passing from one controller to the other, because to achieve this, the robot needs stabilization. And as we started to develop a linear inverted pendulum model together with a zero moment point paradigm that was able to compute the desired trajectory for the robot center of mass and also for its fit location. Here you can see the very first tests that we performed to check the stability of this solution. And we asked rim C to stand on one foot in a stable way. And you can see that he basically moved on one side and then raised the other foot, and it's stable because it kept this position without problems. Next, please, Fabio. Okay, moreover, we tested the same zero moment point plus linear inverted pendulum model in simulation, asking the robot to walk again with this whole body controller. And finally, we added, here you can see the video, we added the BSP as the motion planner as before, and asked again the robot to track this red blob, as we described before. And all worked in simulation, even if some fine tuning should be still performed to improve the robot behavior. But still he can walk, so we were quite happy. So please, next. Next, okay. So in conclusion, we were basically able to demonstrate the impressive robustness and effectiveness of our BSP approach, even applied to a humanoid locomotion. So it's quite powerful. And we were able also to stand on one foot with the real robot and to work in simulation. Future work will be aimed at assessing the BSP performance as a stabilizer, and to compare this new stabilizer based on BSP with the more conventional and employed techniques, MPC and other approaches. So for me, it's all. Thank you very much.
Thank you.
So thank you. Is there any question from the auditorium? Well, I don't complain because I'm afraid you will never ask me again to chair a session because we are running quite late. Maybe, well, you still have time to come up with some question because the next presentation should also be done by Fabio. It's HumaBiMan, bimanual manipulation by DL and fractional control of TO humanoid robot. We're probably going to learn what DL means. I have some ideas, but maybe it's something different.
Okay, so let me share again. Okay, this is another joint work of robots, this time with humanoid labs of a robotics lab at the University Carlos III de Madrid, where actually I've been working for sometimes several years ago. So you may know that, for sure you know that Carlos III has developed over the years a humanoid robot called Theo. This robot is actually a research platform for advanced control, and basically was we wanted to do in this case, like in the other case, we wanted to test a scientific hypothesis by Berthaud, but also to achieve robustness in some tasks that it's needed in everyday life. For example, if you want to use a humanoid in a warehouse. Another thing that a humanoid used in a small warehouse, because we know we have super automated warehouses, but still most of small, medium enterprises have a small human sized and human tailored warehouses, no? Because most workers are humans, so it's a story about humanoids. One of the tasks is for sure to follow some target. Another task is just take this box and put it on a pile, or take the box and hand over to a human. This is exactly what we have implemented in this small project, where again the ingredients are conceptually the same. So there is a whole body controller, there is a linear invented pendulum model. The controller is with respect to also to the previous presentation is different because it's an advanced control which is based on quite advanced approach in merging a fractional PID controller. So again, something that have been researched for many years by the group at the Humanoids lab in Madrid. And with, again, whole body control and the linear invented control model. This is, if you wish, it's quite, again, quite high level presentation with of a controller. But what you should notice is, as you probably expect, that you have both vision control system and a for control based on a sensor torque sensor in the hands. And then it's everything is tuned by a machine learning, reinforcement learning approach. Experiments, you see, we performed basically two. One was to take a box of unknown weight, of course, in a range, and hand it to an operator. And this is the first experiment that I hope I can show you. Sorry, this is putting on a stack. And you see that it could improve, but it's the essence of a task is there. And then, sorry. And this was, sorry, I went too fast with the presentation. This is instead the case of a handover to a human operator of the same box. Actually, of another box of unknown weight. And you see that I think that if you did some test with this kind of handover task, you know, it's not a very easy task. So also this has shown successful. In both cases, we, like also in the previous experiment, we have collected the data, plenty of data, and so we have a solid ground for future work. In the future, what we would try with respect to Theo is to do the same while maybe moving a bit. So the box pile of the operator could be 1 meter away, or perform that on a not perfect floor, because this is again, so if we personally, but I think it's a widely shared opinion in the humanoid community, if where humanoid technology could in principle do the more difference is in everyday human inhabited environments, and those environments are not perfect. They have slippery floors sometimes. So the idea is to address some specific task with the idea that as we progress as a community, we can really fix all. So, and that's all from my side about this project. Hello?
Questions from the auditorium. So maybe I start with one of my questions. The handover, the robot-human handover of the box. Could you elaborate a little bit more on this? Is this kind of open loop, so the human adjusts to the robot, or do you do some detection of the human hands or human position? How do you do this?
Okay, I think Santiago is there, so maybe he can give you a better answer. Santiago?
Yes, Santiago is here, and he got the microphone now.
Okay.
Hello. Well, there is no identification of the human operator in the environment. We have other projects in which there is an interaction between human and robot. But in this case, we only make a vision, we close the loop with the force sensors in the robot and with a vision system outside the robot, because you can see in the picture that the robot has no head in this moment because some critical questions. And we use vision, external vision, to close the control loop with the force to be manipulate the box. But with the oxide operator, there is no kind of closed loop.
Not yet. It's future work.
Yes, of course.
Good. Yeah, any other questions?
Fabio, I was wondering, what exactly is the benchmarking? I was missing so the task is clear, but how do you benchmark this task? What are the criteria? Is safety part of that benchmarking, especially if there's a human there?
Actually, we focused on actually the probability so how many times you perform a task and time for task executions. We didn't address the safety issues in this specific project. So it's...
Was it some trajectory you're following? I just wasn't sure the benchmarking, the objective kind of criteria. Was there?
No, the criteria is to maybe also, Santiago can tell more, but...
Yes.
Santiago.
The benchmarking target in this case is to study the stability during beam manipulation, changing the box features, shape and weight, and as well the trajectories, the ability of the robot to put the box in different heights and in different places.
Okay, any further question? So maybe let's thank again our two presenters. Fabio, thank you for giving us these insights. And we come to the final presentation of today, Matteucci. And Matteo appears to be a very smart guy. He's going to present two projects in one talk. And if I remember correctly, he also presented two posters downstairs, doubling his opportunity. Not? I think it was. Okay, so I'm wrong. Please, Matteo.
Okay, so I'm not smart and I'm not alone. So the presentation will be given together with Vincenzo Suriani, who is with me. And we're going to talk about benchmarking humanoids in everyday tasks. And I would like to start with how we came with this idea. And well, the idea came from these videos, basically, because, I mean, you remember the DARPA challenge, the first one. And it was, I mean, the first videos were kind of funny, but somehow they highlighted how very simple tasks which require the interaction between cognitive capabilities and motion might result much more difficult than what you actually expect. So we started from the beginning, then from this, and we thought about the door as one of the nightmares for our robot. And you see here our Tiago, very scared about opening a door and being conscious that opening a door is not as easy as you might think. So when EUROBENCH came out, we were really intrigued about preparing robots for the real world. And we think, okay, the door is something which is real, and we know it's very difficult for our robot. At the same time, we were running another European project, which is called Shirok. Shirok is a European project which is ending now, so it's perfectly synchronous to EUROBENCH. And it was about competition in smart cities. So we thought about which tasks could be done in smart cities where robots interact with humans. And well, one thing that the robot could do together with the human is to open the door to a person, or, sorry, that was too early, or maybe help a lady at the supermarket with the shopping cart by pushing the shopping cart. And for the door we knew, but we thought that also pushing a shopping cart was a very difficult task. So we decided to propose two benchmarks based on these two tasks to EUROBENCH. And so I'm putting here the EUROBENCH logo next to the Shirok logo because it was a cooperation. Please notice how our designers have been biased in the choice of colors. I mean, I just noticed this here. I mean, that there might be some hidden bias behind the choice of the color. I have some clue about this bias, but I will not tell you later. So what is this benchmark about? I thought that giving you a sort of stop motion video of this would help. So I will do this for the MADROB, which is the door-based, and then I will be more brief on the other one. And the idea is that our robot needs to first navigate to the door, so it has to perceive the door, then has to localize the handle, which is a specific object which, I mean, can have different appearances and different ways of interacting with it based on the appearance. And then has to operate the handle. I mean, not an easy task, but at the end you will be able to open the door and interact the door to open the door. Opening the door, interacting the door might be not so simple because we decided to make it more difficult, like actuating the door with a motor and a sensor so that we could simulate some unexpected conditions, like a box behind the door that you have to push, or a cat behind. What is different between the cat and the box is that when you push the cat, then it goes away. So you see that it has two different impedances, and you can program these different curves. And then you have to navigate through the door, which means going through a narrow passage. Well, depending on the size of your robot, might be more or less narrow. And finally, I mean, you have to close the door to complete the task. So that's the idea of the benchmark, and among the other things, we are timing it and checking how long does it take to do this. I already talked about this active door by posing some force. To measure the force exchanged between the robot and the door, we instrumented the handle also of the door, so you can measure how much force has been exchanged with the handle of the door. So I'm talking here about two benchmarks. One is MADROB, which is this actuated door where the robot has to unlock and open the door, which has different door behaviors and different difficulties that you can program and just pass through. And the other one is the trolley assistant, which means, again, to grasping a handle, a sensorized handle, and exchange forces with the trolley to push the trolley along a path. And the nice thing is that when you have a trolley, you can easily control the weight. You just put more weight into the trolley. But we are more mean, and so we actuated the trolley so to simulate those difficulties that every day you find at the supermarket, like one wheel which is stuck and the robot goes in one direction instead of another one. So I take the opportunity of this slide to introduce the partners of this project, which are Politecnico di Milano, the university I come from, Sapienza University of Rome, Vincenzo comes from that, and then we have Istituto Tecnico Superiore of Lisboa and Nova Labs, which is a startup that has helped us in the building of the two benchmarks. So what about MADROB? As I said, MADROB stands for Modular Active Door for Robot Benchmarking. It's an hinged door which can measure the angle and the forces exchanged through the handle, and it can simulate by moving profiles different types of doors, maybe the presence of objects and so on. I will talk a little bit later about experiment and simulation. This is some example of the building of the door. On the left, you see the frame, then you see the size. You see a set of handles, so you can exchange any of those. So basically, the door has been prepared in order to put different kind of standard handles, so you can make it more difficult. I think that the more difficult one is the white handle on the white door. I mean, that makes interesting difficulties to perception as well. And you see also the actuated and handler with the force sensors. Once you cover the door, I mean, it looks perfectly like a normal door over there. We also took advantage of the fact that we were running in parallel two projects, the Zereik and the EUROBENCH. So in the September of 2099, we had the first event in Milton Keynes. So we took the opportunity to show and demo the door in a, let's say, context with some robot. As you see, not all the robots were really interested in participating, but some of them did. And you see here one of the robots. I think this is the Toshiba robot that is used for the standard league in RoboCup at home. So they were participating to the competition. You see that robot interaction with a handle is way less natural than what we expect, at least this kind of robot, but I'm pretty sure that the more we will start interacting with everyday object, we will see more natural interaction with handles and other objects. The other benchmark I'm talking about is Beast, and Beast is basically an actuated shopping trolley with 2 actuated wheels, and those actuated wheels are used to perform some disturbances and program some friction on the ground or introduce some, let's say, disturbance on the pushing. You can have, you have, let's say, a path to follow. So you have, I mean, to make a dexterous maneuver while pushing the cart, and you can load on the shopping cart some weight in order to change the difficulty of the task. These are some close-up. You see that we have sensors on top of it because we have also a localization problem, and we have to give a feedback to the robot on where the cart is. I see people which are really interested. No, we didn't install a trolley in a supermarket. I mean, we bought a new one, so don't worry. No one will chase EUROBENCH people for this. Okay, on the right you see the handle. Again, we have load cells. We have 2 load cells to understand how balanced is the exchange of forces to the trolley. Again, we had 2 parallel projects, and both suffered COVID delays. But last September, we managed to have another event of Xerox, this time in Bologna, from the planned originally from the 6th to the 11th of September, but then it was run between the 8th and the 9th. It was in a very nice ancient building, was Palazzo del Re, and here you see the benchmark set up and tested, again, in this case with the Tiago robot at the time. I mean, this has been the first public robotic competition post-COVID ever. I mean, we were totally happy about this. I mean, I will conclude my part of the talk, then I will leave the stage to Vincenzo with the question that many of you might already want to ask. So where could I find them? I mean, where are these benchmarks? So these benchmarks are in Genova. They have been set up a month ago or a couple of months ago. Here the picture of the Genova facility, and you can spot on the left the Beast testing, and on the right the MADROB testing. But you might not want to go to Genova. Well, you should go to Genova first. So you would like to have this benchmark with you, maybe like with the Newton's Commander, to take the benchmark with you in your suitcase. And that's why we also made 2 simulations out of this test. And that will be the part that Vincenzo will talk about, and then we will answer your question afterwards. Please, Vincenzo.
Okay, so yes, I'm from Sapienza University of Rome, and I'm going to present the part of the simulation. So yes, actually in each environment in which there is a robot, actually having a simulation environment helps a lot, because in order to do not break the robot and to test approaches on the real robot, it's better to have a sandbox where to try things. And so we developed this simulation environment as close as possible to the real one, in order to be able to simulate each physical interaction with the door in the left case and with the trolley in the other case. And to this end, I will start talking about MADROB. And in MADROB, we have this active door that keeps all the features of the real door. But actually, there are more features because this is a special door, as was mentioned before. And in fact, this door has, for example, the possibility to choose the side in which it has been open, to choose the capabilities of the handle. And so we had two actually active elements. One is the door, and the other is the handle. And I'm going to present briefly the architecture. And so actually, we left all the part that has been developed for the real robot, that is the blue one, as it is. So actually, the simulation and the real robot are perfectly compatible with the same benchmarking system and the same performance indicator. And so we developed a simulation, an extension of Gazebo in order to extend the capabilities in the joint simulation, and then a middleware that is a layer that we use to adapt things to the EUROBENCH software base. And so if we start from the door, actually in the real door there were a rack of 16 sensors that were placed above the door. And those were made to express exactly the position of the robot and the capabilities in traversing the door space. And so we developed this custom sensor and the sensor for the encoder together in order to provide the same kind of responses in the benchmark system. And about the handle, actually, we tried to be as close as possible, close to the real one. So instead of having an instantaneous unlock of the door, we designed a physical handle, in the simulation way, in order to be able to simulate, as you can see there, the door latch that was able to open the door only if physically was not blocking the aperture of the door. And so actually we implement this inside of our door, and with 3 reference angles which were made public in order to be allow the robot to be able to open the door at the precise angle. And then we integrate everything with the simulation, the MADROB interface. So here, for example, in the MADROB, you were able to record and report the status of the door, the status of the robot approaching side, the benchmark type. Here, we change this kind of paradigm. So instead of using the GUI to report things, the GUI has been used to set up the simulation. So instead of settings the field as they were in the simulation, the GUI was able to change dynamically the simulation parameters and then to record and replay the benchmark tests. And so even here we have a different, this is the door in the final scenario, so inside a building, and here you can see that there are the cameras of the robot and all the plot for the topic that the robot was able to perceive. And here we can see that we have different, as in the real case, we have different force profile applied to the hinge of the door. So we have no forces, constant forces, sudden ramp, wind ramp, and sudden force. So we were able to simulate the wind on the hinge of the door thanks to the plugin of the extension of Gazebo that I was talking about before. And so here we have a little overview of the whole system, and this is actually the interface here that was made available for the team participating in the competition in order to develop behavior and controlling system for the robot to open the door. So here you can see just our attempt in doing the door aperture, the door opening. And So here, this is the whole hinge actually, and then the whole handle, we try with 2 different handles. And here you can see that there is the plot of the handle aperture and of the door data from the interface. And about BEAST, actually we follow the same paradigm. And even here we try to be as close as possible to the real one. And so here we developed 2 different trolley. One is the shopping cart. The other one is a walker for elderly people. And we provide both the environment. I'm just talking about the first one. And here we have a similar approach because in order to do not change the BEAST software base, actually we introduced this middleware that was made to make things equal with the real one, and then the simulation environment at the extension of Gazebo. Here actually there are different sensors and different capabilities and different performance indicator. In fact, as with the real case, we had the laser, the active cart. In fact, in order to have disturbances, we had to include motors, so to speak, or active joint in the cart. And then we had sensorized handle for the cart in order to record the pressure and the torque that the robot was performing on the cart. And so these are 2 screens of the interface. And for example, here we have, as in the previous case, but differently, we have sudden force as disturbance force and the load. So actually, through the interface, possible even to set up if in the cart there should be a load or not, a loading or not. And then there is the possibility to make the robot already with the hand on the handle of the cart or not. And so this is a brief representation of what happened. And the interface, actually, robot is not moving because that was part of the benchmark. So was asked the team participating in the competition to move the robot, so we just moved the cart since it was active. And just to show you how the experiment should have be done, and here you can see that there are some regions of the area that have to be activated with the cart, so passing through some checkpoints. And there is the reporting of the forces on the cart and so on. And actually there is this path that has to be done in a 8 form, and in which all the checkpoint has to be colored in order to close the benchmark. Actually, there is even the time that it's quite important because it's one of the performance indicators. And so at the end, we had a team participating in the competition, and each of those had the chance to test and to try things in the simulation in order to be ready for the real one. So thank you for the attention.
Yeah, thanks again. Are there any questions from the auditorium? No questions? Oh, wow, okay. Maybe we start on this side.
Hi, thank you. Very interesting. I was wondering, in both setup, vision is involved to localize the handles, both handles. Is there a way to skip it? Because at the end, if you want to validate the manipulation, of course, if you can localize and manipulate, it's better, but if you just want to focus on the manipulation.
Yes, somehow. In a sense that, for instance, the example in the angle that we gave, the small video with the Toyota robot, they basically measure the position of the handle. So basically they use the absolute position of the handle to program the motion. So in that case, there was no vision involved at all. For the cart is more tricky in a sense. If well, I will not go back to the slide, but if you check in the small picture that I took, they had put like an R tag on the cart in order to easily detect the position of the cart. There is another important thing is that to perform the control of the cart, you need to know the relative angle between the cart and the robot, because I mean, usually you need to control that variable, so it is very important in that. So for the door, I mean, it's a fixed object, so it's okay. For the cart, the relative position between the robot and the cart is a difficult thing. The position of the cart in the environment, we can communicate through the laser. So we have a localization algorithm on the cart running, which tells the position of the cart to the robot. But the relative position, that's difficult, you're right, perfectly correct.
Thank you. Thank you. Very nice presentation. I'm happy for this synergy between the EUROBENCH and the C-ROC project. I'm curious about the simulation environments, and also, so first question is how good is the simulation environment with respect to real life? Is it replicates this or not? What's your experience? And also, what's your feedback from the participants to these competitions? Do they then gave you any feedback on the platform, on the test bed? What's your feeling about?
I will ask the second first, and then I will leave you the first one, which is the difficult part. So we tested the physical object in the competition, not the benchmarking structure. So basically, the door was ready before the software and all the rest. The feedback was that these are difficult tasks. Especially the cart is much more difficult than what we expected. Also because of interaction between the kinematic of the cart and the kinematic of the robot. Because you don't have just to plan about your motion, but about the motion of another object because of the push which is induced by your motion. I think it will be an open challenge for a long time, that one, more than the door. That's my... I see.
Yeah, I can say something on this, because actually the beast was tried already by University of Bonn robot.
Ah, okay.
And these problems that you talk was easily solved actually by adding some passive compliance between the end effectors of the robot and the trolley, and it was possible to complete the challenge actually.
Yes.
And yeah, of course, but it's a problem if the robot is stiff and they cannot really adjust the compliance on the arms. Yes.
Yeah, exactly. As for the simulation,
it's a hard question actually, because we try our best in order to gap the so-called sim to real gap, but to bridge this gap. But actually, for example, we discovered that was even using the capabilities of gazebo about simulating joint and disturbances, we had to extend by writing the C++ plugin for gazebo in order to have more realistic disturbances on the hinge. But still, it was an attempt in order to reduce this gap, but we were for sure there is plenty of room to improve. So we try our best in that direction, but still there is plenty of room to improve.
Yes. With the following on this, there is an anecdote that we have is called the Nardi effect. Nardi is Professor Nardi from Sapienza. Then he tested for the first time, the first person, the door, and nothing worked because of the torsion that you could put on the handle, because this might generate a torsion on the structure of the handle. We had to make it more stiff. And this is totally not modeled in the simulator. So the torsion of pieces and the compliances, as Nikos was saying, they are not simulated. And this makes a huge difference between simulation and reality. Sometimes in favor of reality, sometimes not, if we think about stability. So I think that, yes, there is a gap. What I can say that if it does not work in simulation, it's very hard that it will work for real. The other way around, not necessarily.
Sometimes happens also the other way around.
Yes, sometimes it happens. Yes, that's true. Friction, compliance, they help, yes.
Well, this seems to be a very interesting subject. According to my schedule, there will be a coffee break. So maybe there's the opportunity to discuss some of these things then. However, I have some closing remark, especially on Skyrock. I remember when they applied for the funding, we also applied for funding with a project on benchmarking competitions. But apparently at that time, there weren't sufficiently many European competitions, so they funded the competition first. But maybe for the future, we can have a benchmarking of competitions, robotic competitions. So, Diego, since you pay for the coffee, would you like to say something?
Yes, 11 we come back here. That's the only... and enjoy the coffee. we can start the last session of the EUROBENCH Summit. This session will be chaired by Eric Prinsen and Anthony Remesey, which are the two persons that have been key for the project. Eric has been working on generating data from humans and also protocol and performance indicators due to their experience in the testing prosthesis and exoskeleton robots in the Rossing Research and Development Center. And Anthony, also a pillar of the project, the person behind the curtain of the EUROBENCH software. So I'd like to thank you for everything and also for sharing this session.
Yes, thank you, Jago, and all welcome to this wearable robots session. I'd like to kick off with the first speaker. It's Eduard Fosch-Villaronga about the PROPELLING project. Eduard, the floor is yours.
Hi, everyone. I'm Edward, and before to start, I wanted to ask you how many of you have been in contact with the world of standards? Only one, two. And do you usually feel that the standards are good to go, or do you think that sometimes they are not that clear? Yeah, not that clear, so. That's great. So today I'm going to talk a little bit about our project that it's called PROPELLING. I'm going to talk about a little bit of the bigger idea on science for robot policy, the experiments that we had, the framework, and also accounting for diversity. So in the project, we've been working with lower limb exoskeletons, so that has been our environment. And this robot technology, of course, you're very familiar with. They help wheelchair users and other patients to stand up and walk. And this is a technology that it is so new that current standards and policies might not 100% or fully represent because they are very new. They're so new that the EUROBENCH project started with the very big idea and ambition of creating the first benchmarking framework for robotic systems in Europe. And while we thought that was a great idea, to create different tests so that people could come and improve their robot devices, what we were doing in PROPELLING, which stands for Pushing Forward Robot Development for Lawmaking, was basically to say, well, maybe what we could do is to use these testing zones to generate policy-relevant data that then we could put forward to standardization organizations or to relevant policymakers so that then we could help in improving the standards that are governing these devices. So in short, what we try to do is to work on science for robot policies. And the two main aspects that we wanted to zoom in when we were working in PROPELLING was the fear of falling. There's subjects that they haven't been walking for some time and that they might be put into an exoskeleton. They may be afraid of falling. And rightfully so, one of the risks of wearing a lower limb exoskeleton may be to fall. So we wanted to understand whether that could be considered a safety hazard. But also we wanted to expand the knowledge on protective stops, because it is not very clear what you need to do before the protective stop is going to be activated, or the emergency stop, and what are the safeguards that you need to do in order once they are there. So during our first week of testing, we invited a subject with a health condition, GWS, that he came with his family to the testing zone, and the idea was to perform certain experiments that we had with him. But we also had other subjects. Mainly, we had also Casa, which has been working with us also in the project. And then while we were conducting the experiments, we started realizing that Hadassah started complaining about the device, like it was hurting her. And she was complaining that the device was hurting on her hips and that it was like also pressuring also in the breast area. It was doing a very incredible noise. And when we tried to do the experiments with, and what we realized also is that then when we started looking at the different levels is that we started seeing that the male subject and the female subject had different energy expenditure, but also the stress levels. Of course, this was just like for a couple of subjects, but we started like seeing that they were a little bit different. And when we tried to do this with the subject with a condition, then we realized that we couldn't really perform the experiments. The user was very heavy. The device that we had could not really support his weight, and the facility at that time was not very much prepared to accommodate that, which to us, it was a little bit surprising because we thought that these robots would, the main idea was also like to help patients with a condition. But that was our main basis, no? And then like what we started to think is that, okay, it seems that there are different categories of users that they are going to be testing this robot technology, that they might have different needs. And although we wanted to explore the fear of falling and the protective stops, then we were puzzled a little bit like by how then this diversity was being included into these devices. So what we did is like to look at different frameworks that they try to put forward some physical safety requirements for robots technologies, and we were in particularly zooming in the ISO 13482 on personal care robots, which governs personal care robots, including mobile servant robots, person carrier robots, and physical assistive robotics. And the standard mainly deals with physical aspects, basically because the threat of a physical harm to a person is an ever-present concern. But with some researchers at the University of Twente, what we were trying to see is that safety is a very large concept in which it can have a physical dimension, but that when we are interacting with these machines, there's actually a much more complex dimension to safety. There is like the safety with respect to the social interaction, the physical interaction, the cyber-physical aspects, but also the temporal aspects to that. But what we realized is that the standard didn't really accommodate for diversity aspects, and we refer to diversity to the practice or quality of including or involving people from a range of different social and ethnic backgrounds and so on. And what we saw in Precise is that when you look at the standard in the introduction, basically it says that future editions of this international standard would include more specific requirements on particular types of personal care robots, but also on different categories of people like children, elderly persons, and pregnant women. So although the standard at that time in 2014 already acknowledged that these type of categories of people would deserve different safeguards, the standard like didn't go that route. So basically what we know is that basically users come with different shapes and sizes, and even with children we know that basically instead of like learning how to restore a lost function, they need to learn how to walk. So the fundamentals of like the main task of the robot are a little bit different. And together with a colleague, we were trying to look at this from an intersectional point of view, so to see like how these different shapes, sizes, gender, and sex could actually play a role into how we design a robot technology. So just for your information, in 2020, the ISO standard was revised and being untouched, as if somehow these subjects or these different categories of people did not really deserve a little bit of more guidance in this respect. So for our second week of testing, what we thought is like, okay, we need to have much more subjects to understand whether actually there is a difference between gender and sex, and how that applies to robot technology. So what we managed to have is to have 16 different subjects, in which we had 50-50. So like in this time, we managed to have different sexes and genders. And what we realized is that actually 3 subjects, they could not do the experiments due to actually diversity considerations. One, because there was like a male subject that had a bigger complexion, so like the device basically could not fit him. And then like 2 female subjects, one with a very large breast and another one that with a very, very small trunk, so that the device was not fitting her. And what we try to do, it is actually to work again on the protective stops idea. So like basically what we tried to do was in different of the protocols, trying to press the protective stop to see how the users would react. And we would do that with the with the bench, but also in the slopes. Basically, we wanted to know how then the users would react, and then like how they would experience then the protective stop. So down below in our poster session, you have a lot of QR codes if you want to see our long report on that. But just like to give you very briefly what we understood for just this very small universe of people, that the subjects experience protective stops differently, and these vary largely between different sexes. That there are apparent intersectional aspects that currently they are not being accommodated between the device that we were using, but also the test bed. That there are critical moments in which a protective stop would significantly endanger more the operation of the user, mainly when climbing stairs. And also that the cyber-physical nature of the robot actually could actually be a cause for activating such a protective stop, basically because then the robot would start doing very funny movements, and then that would actually trigger the emergency stop. Just to continue, we also realized that it's not very clear how much the users can be in a certain position when the protective stop is being activated. Imagine that you are actually trying to get up from a chair, and then the device is being stopped, and then like in that moment, basically the users can be around 1 minute being waiting, but then there is a moment in which they start fainting. That in the slopes, actually, like the walk speed actually increased the confidence that the users had. So like the faster they went, then when the protective stop was activated, they didn't feel that it was like as dangerous as when they were going slower, and that the users are not very clear on which are the safeguards that they want to have. Some of them, they report that they would like to have like a hook in the ceiling. Some of them, they say that they would like to have some bars. But what we know is that they were very confident to know that there was like someone behind them, like in order to wait for them. So just to close up in here, what we started to know is that maybe we need to start thinking a little bit about diversity and inclusion. It is a topic that might not be that straightforward when it comes to this community, especially because of the traditional configuration of the field. Usually there are white males working on this, although of course we've seen that here in the Hospital Los Madrones there's a lot of also women working on this. But also because for many different reasons, women have also a longer life expectancy. So we have the impression that maybe they are going to be the ones that they might need more these devices. I actually really wonder why like this may be the case. But basically, what we know for sure is that accounting for sex and gender differences makes for better science, and we have seen this in different domains of application, like concerning the dummies for car crashes, but also for different appeals and drugs. And that in this field, diversity in robotics and artificial intelligence may work as a double-edged sword, in which, like, for one side, it can help exacerbate certain biases that we have, but on the other side, like, it might be also a moment in which we could take advantage of mitigating some of them. Thanks to all of this knowledge that we had, like what we tried to put forward is also a protocol. We were part of the second generation of FSTPs, so we didn't do any protocol. So like what we tried to do it is like to try to modify a little bit the different protocols that we had. So we proposed like to have one on protective stops, and just as main takeaways on this is that on our way to try to generate policy-relevant data to expand the knowledge on fear of falling and also protective stops, we encountered with these gender and sex dimensions that we were really not expecting, but that we understood that had a very much more prominent role than first expected, and that we do not have that much data in this respect. So if you ever are working on different subjects, I would very much recommend you to also test in different sizes and also in different women, and then try to understand how the subjects can need to be accommodated on this. And that these diversity dimensions need to be on the test design and the skeleton, but also in the laws and technical standards and policy. So thank you so much for your attention. If you want to be in touch or want to know more, just contact us. Thank you so much.
Thank you so much for this interesting presentations. Are there any questions from the audience? Yeah, there's one, at least from Jan.
Yeah, thanks, Eduard. Very nice presentation and all very relevant points, I would say. I would also ask, what do you think is the proper way to address them? Because putting it in a standard also doesn't mean that the problem is solved. It's also attention of the design community, yeah. Regulation maybe. And I'm more from the medical device side, and there you are required to define very precisely what is your patient, and also physical dimensions and sex. And yeah. But do you think that's an example, like the medical device? Because it's also very open, but yeah. In the end.
So I think that both. So on the one side, I think that usually from the legal community, we usually call upon designers and developers saying, oh, you didn't take into account that. But then when we looked at the frameworks, we thought, oh, but this is actually not that much here. And yesterday with Gurvinder, we were talking, and he said, oh, but there's another standard that talks about human body and sizes. And that is also one of the problems of the standards. Now you have way too many, and you do not know really which ones you need to follow. So in the law, we say that a law should have or provide legal certainty. So which means that every piece of law should be as comprehensive as possible, so that then there's no way or there's no room for developers to deviate from that. So that is one point. So like having policies that have that more expressly would actually make an express obligation for developers to account for those. But then also, yes, another problem that we have in the law is that basically we don't have that many robots. We have medical devices, we have products, we have machinery, but there we don't have this personal care robot category. With Gurvinder also we talked largely on that, on the confusion categories of these standards. My recommendation would be to try to be as diverse as possible, because what we realize is that actually the majority of the measurements that we have, and you can check that in the protocols, they do not include, for instance, breast size. So they have very objective measurements, and in some of the deliverables that we have there the measurements. They are there, they are just numbers, they are bones, they are no wristband and so, but not breast size. And that was actually an excluding factor for certain women. And we don't want that, right? And then what we started to understand is that, well, maybe having an adjustable device is not enough to actually make these devices inclusive and accessible to many.
Okay. Maybe time for one small question. I don't know.
I was just going to just highlight what Jan asked about the medical and the non-medical. Because you've used the 13482, which is the non-medical, but then your subject was clearly a medical, and so you.
In the first week, yes, but not in the second week. So yeah, and
so you should use the 278,
okay,
which is the IC, is the medical device. Actually, Jan was the project leader for that, so he developed that. So that is looking at medical exoskeletons.
Yeah, it's true. Yeah.
Okay, so
yeah.
So make sure But I'm very encouraged that you're the first speaker who focused on safety. So we as researchers tend to focus on performance. Mm-hmm. And performance, okay, is very important, but safety is even more important. Yeah. So for God's sake, make sure your system is safe.
Yeah, and the thing is that what we do not know is actually whether some of these aspects are safety related or safety critical, and that's why we do need to have
understand risk assessment, understand risk mitigation, all those things, and then worry about performance. Yeah. Thank you.
Perfect.
Thank you again. Thank you again, Eduard, and I think that's a great conclusion to the first talk.
Okay, so the next talk will be done by Antonio De Lama about project intention. Oh, it's you and it's not Antonio. Okay, sorry.
Okay, hello everyone. I'm Manuel Fernandez. I will present you the intention project. This intention project is formed by Susana Borrego, Cristina Rodriguez, Camila Rodriguez, and Antonio José de Lama from the University Rey Juan Carlos. This project belongs from the second phase of the European project based matching, EUROBENCH. The objective of the intention project was to compare the effect of human exoskeleton interaction as well as the user perception using different control assistants, being the joint trajectory tracking, the joint mechanical admittance controller, and EMG triggers controller. Our hypothesis is the use of the EMG-Onset trigger controller will improve the human exoskeleton interaction in comparison with the other two, the admittance and trajectory one. With this purpose, we designed 3 different controller strategies. The first one are the trajectory controller, in which consists to make a continuous working trigger where the controller is tracking the current joint angle for produce the next angle in order to produce a strictly working assistant trajectory. In this way, the human tries to follow this assistant. The second one are the admittance controller. In this strategy, we focus in design, improve the compliance of the actuation. We made this adding an angle of tolerance in which the controller allows to perform a range of deviation during the working trajectory. In this way, the human has the capability for follow a more flexible human walking assistant trajectory in comparison with the previous one. The third one are the EMG-Onset controller, in which focusing involve the human inside of the loop of the controller process. We achieve this using the muscle activation for trigger each step. Once the step is triggered, we follow the admittance controller strategy for control the assistant working trajectory. For this, the experimental setup for this experiment consists to combine the three different setups. The first one is the exoskeleton setup, using the exoskeleton H3 and its device. Both is using for record the EMG, the onset trigger, and the joy angle. Both those devices are connected directly with the PC-10-4, which are synchronized with the training and the experience protocol. In the experience space matching is used for record the heart rate, respiratory rate, galvanic skin response, and the perception of the user by a questionnaire. And finally, we use the Pepato space matching for analyze the sanity of the EMG. This is how it looks like the real setup. We have the participant inside of the exoskeleton on top of the treadmill, controlled by a computer that controls the speed of this wall, and have the computer that controls that synchronize the experience device, and behind the computer, the PC-10-4 that controls the exoskeleton and its device as the same the controller trajectory. We have to record the 12 muscles, being 6 for each side, being the rectus femoris, vasto lateralis, and the tibials from the front side, and the back side we have the biceps femoris and soleus and gastrocnemius. All of them are connected with each device in the orange device on the back, and also we have the experience device, which are in the left wrist the galvanic skin, and under the clothes the band which is able to record at the same time the heart rate and the respiratory rate. Okay. The protocol using in this experiment is followed first begins with the instrumentation, followed by a resting phase, using for the participant for calm down and relax his heart rate. After the resting phase, we start with the 3 different controllers. The order of this controller is selected by random, and before to start any controller, it requires a previous training phase. This training phase is used for the participant familiarized with the different assistant trajectory control. After 4 minutes of controller, the participant need to fill the questionnaire related with the specific controller. Between different controllers, it requires 5 minutes of rest for relax and calm down during the stretch of the different controllers. In the case of the onset controller, the last one, we need to add a previous phase for establish the threshold parameter. This threshold corresponds to the point when we consider the amplitude when the muscle is activated. This point is used, this activation is used for trigger the step. After conclude all 3 experiments or 3 controllers, the participant fill the rest of the questionnaire. For this experiment, we recruit 14 healthy volunteers. Here I will show you a brief video on we represent a participant with the 3 different controllers. The first one is the trajectory 1, in which the exoskeleton produces a restricted walking assistant trajectory, and the human tries to follow this trajectory. The second one are the admittance controller, where the exoskeleton, in this case, produces a more flexible working trajectory. And the third one are the EMG-Onset controller, and in this case, the participant has to activate the muscle, especially the rectus femoris and the contralateral soleus, for trigger the step. Okay. So as said before, we recruit 14 healthy volunteers. However, due to a problem with the experience device and in relating with the data format and synchronization between protocols, we'll only obtain 7 healthy participants with the correct result in the 3 scenarios. Sorry. Relating with the exoskeleton result, we obtain the angle of the 3 different joints on both sides, and we saw clearly in the angle ones, when the participant used the trajectory controller, we obtain a higher range of motion. Here in this table, we represent the maximum, minimum, and radial motion in the different joints. We remark we assign with a 1 when the statistical differentiation between the trajectory controller between the admittance controller, with a 2 statistical differentiation between the trajectory and onset controller, and 3 with differentiation between admittance controller and onset controller. We can show the trajectory controller are present a statistical differentiation between the other 2. This is why, because the trajectory one is produce a more strict trajectory and obligates to the participant or the user to perform the all range of motion. This indicates at the same time the admittance controller and onset controller perform a more flexible working strategy. With respect with the experience software, we obtain 4 performance indicators, being the attention, energy expenditure, and fatigue and stress. However, we can establish a statistical differentiation between the working conditions. But in corresponding with the onset controller, we can show that require less attention and produce less stress in the patient, but at the same time produce more energy expenditure and fatigue in respect to the other 2 conditions. As I repeat, we can find a statistical differentiation between different conditions. Relating with the questionnaire that represent the user experience, the user perception, we can obtain other 4 conditions, being the acceptability, the functionality, the perceptibility, and usability. These performance are scored from 0 to 7. Mark the lower one in the perceptibility that correspond the confidence of the participant inside of the skeleton. And the side of the physiological metric, we can establish a statistical difference between the working conditions. Regarding with the Pepato software, we use 3 synergies for analyze the 6 muscles of the side of the left leg, and we obtain a VAF of 0.9. That corresponds the quality of the EMG reconstruction. As summary, we can observe that the onset controller produce a lower duration of the peak of the activation in comparison with the other 2 controllers, the trajectory one and the admittance controller, and produce a brief delay in comparison with the other one. This is why we suggest this, because the participant or the user have to activate in a specific time the muscle for trigger the step. Regarding the EMG data, we can show the amplitude of the soleus is higher when the subject uses the onset controller. This is why, as I said before, he has to activate this muscle for trigger the step. At the same time, we can show in the rectus femoris the activation is higher when you use the trajectory one. This is because, as I said before, the trajectory obligates the human produce the higher amplitude of the trajectory, and this muscle is clearly associated with the amplitude of the step. For other hand, we successfully conclude the timing of the onset are corresponding with the initial phase of the literature. And additionally, we can show the user activate in the most of the case the soleus in comparison with the rectus femoris. In conclusion, with the support of the facility staff, we have to overcome the learning curve or use the experience and PEPATO protocols. However, we suffer a loss of data because the early use of the software and the combination of the protocols. Regarding with the intention project, we obtain, as we expect, the admittance controllers and onset controller allows a more flexible on cinematics with respect to the trajectory control. Such flexibility was reflected in the mean muscle activation and correlation that correspond with the PEPATO result. And in addition, the onset controller altered the muscle pattern, although we have a lack of statistical powerful. Additionally, such flexibility doesn't reflect in the physiological metric that the experience result, and didn't impact enough in the user perception experience, perception. But in the other hand, we obtain a successful result with the onset controller, which has been able to land the step in timing expected by the literature. For ongoing work, we have to compare these results with an implanted EMG electrode and adapt this, and use this experiment in patients with incomplete spinal cord injuries. Thank you very much for your attention.
Thank you. Is there any question? Yes. Yes.
Thank you for a nice presentation. Thank you for a nice presentation. Yeah, now it works. I think it's very nice benchmarking example, but it's also remarkable that you see difference in the trajectory, but not in the user experience, basically. So the question is then, what would be the conclusion from that? Like, is it not important what your controller is doing for the user experience, or how would you link these results together?
Sorry, can we repeat? I can hear you. So.
Sorry, I'd say it's a very nice benchmarking experiment, and you see that there is clear differences in EMG and in trajectory of walking of the patients, but at the same or the persons. But at the same time, you see that the user experience, it doesn't make a difference, basically. Okay. And how do you link that together? Does that mean it's not important?
I thought this because the inexperience of the participant with an exoskeleton will affect in this perception, because because using an exoskeleton with your healthy patient is different than be strict in movement with a skeleton. And this affect that, and this is the difference, they have a low mark in the low score in the perception, but the difference between the controller is significant.
Yeah, thank you very much for your presentation. I think it's very important to try to link the control algorithm to outcome of the exoskeleton. I think that's a very important research topic. I was wondering, because I assume that you showed pictures of the whole group, whether there were also difference between on an individual level, because especially if you look at incomplete spinal cord injury patients, they can be quite different, have different possibilities maybe to walk. So maybe if the control algorithm is also the influence, of the control algorithm is individual, maybe we should also look in optimal control, different control algorithms might also be more important on an individual level.
Could be more important because, yes, the use of different controllers is improve the different trajectory because the involve the human in the loop is provide more safety and more confidence with using the specific trajectory in the different or follow and try an extra trajectory that you doesn't control.
Quite interesting with the EMG. I'm kind of wondering, because there are many different types of sensory inputs have been used in exoskeletons. So I was kind of wondering, did you consider including all those other ones as well as adding the EMG? You know, how to enrich the sensory inputs to the exoskeleton rather than going for just the EMG?
Of course, as much sensors you have, more
correct,
more power trajectory we can perform, but have at the same time have the complexity of combine and synchronize the different sensors. But using, for example, I don't know, the image or real-time image, we can record or stimulate, for example, stimulate the muscle. We can in patching, we can force or improve the rehabilitation process.
Well, the reason I kind of say that is because I mean there are some people who kind of don't believe EMG signals work. Okay, so
no,
so it's kind of a.
I know
there are some doubts about that.
It's complicated because it need to filter and a lot of process for real time, and in real time it's very difficult to make the necessary software or necessary processing for improve the process. But it's same. The EMD is very complicated to use.
Very complicated. Yeah. Okay. Thank you.
Thanks.
Thank you very much. So we'll go to the next presentation about PELLEXER project, performance evaluation of exoskeleton for emergency response forces, presented apparently remotely by Jonas Dülberg. You can start, Jonas, if you can hear us. We cannot hear you. So you can hear us on your side?
I can hear you.
And we can hear you now, so you can, please, you can start.
Okay.
Okay.
So, okay, go back. So, yeah, welcome to our presentation. Unfortunately, it has to be remote since both my slides too and from Madrid has been cancelled. But I'm glad to show it to you via Zoom. And yes, the project is called the PELLEXER project. My name is Jonas Dülberg, so I'm a medical engineer and physiotherapist, and I'm responsible for the testing done inside the PELLEXER project. And the PELLEXER project is, as you already mentioned, called the abbreviation for Performance Evaluation of Lower Limb Exoskeleton for Emergency Response Forces. We are located in Germany, and we are part of the University of Applied Science Aachen. And here on the right side, you can see a picture of how it looks like, what we did. So first of all, I would like to introduce our exoskeleton. You can see it here on the right side moving on a treadmill. And Exoforce, so this is what we call our exoskeleton, is an exoskeleton for authorities and organizations with safety tasks. So it's again an abbreviation. P2 stands for prototype 2. And this exoskeleton is just for healthy users. So it's an active exoskeleton for the lower limb, but only covers the movement of the knee. It's always reacting to the user, so we don't introduce movement to the exoskeleton. Just stays as it is until you move to the detect movement, and then helps you moving and will increase your force on your leg. So that's the exoskeleton, and I would like to jump immediately into the test. So we did some variety of tests. So the first one is the so-called step-by-step test, where you perform a dual task. You walk up and down stairs and get cognitive tests to fulfill. And in this case, it was getting a phrase or a word and then saying, have I heard it before or not? And as you can see on the left side, I hope the resolution is good enough, you can see there is not much difference in the performance. So we did not just perform with and without the exoskeleton, we also made a test with the exoskeleton and added payload. This was a 15-kilogram backpack. And there's not much difference, and there's no trend you can discover. The scale here is for correct answers from 95 to 100%, and there's not much variation in there. The total time stays similar within a subject, so black is subject 2, gray is subject 1. And the response time didn't change that much. So our conclusion is, yeah, it doesn't impede you very much. So you are still free to do everything, especially cognitive in this part, and we are pretty happy with the results. But yeah, 2 subjects is not that much. Still happy with the results. The next thing we did was the experience test, where we walk on a treadmill for a couple of minutes and then measure skin response, measure heart rate, breathing rate, and there's questionnaire. And here we also didn't have a noticeable difference between using the exoskeleton and not using the exoskeleton and using the exoskeleton with payload. But here we have to say the number of 2 subjects is definitely, because like both curves show the opposite. If one curve goes down from subject 1, the curve from subject 2 goes up. So like we can say with the number of 2 subjects is basically a match, to be honest, and we had the corrupted data set for subject 1. So yeah, we didn't find the difference really, but we can't prove it in data, so I'm really sorry, but yeah, we had quite fun doing this test. The next test is, as we already heard, it's a collaboration with the PROPELLING project. So it's about safety things within the development, and I'm very thankful for them for connecting with us, giving us the idea to doing such tests. So we here, as you can see, we changed our exoskeleton and made a remote protective stop. So whenever we walked in on the stairs, we just had someone at the side deactivating the exoskeleton at random moments, and we tried to figure out how do we react. And we also gave our experience to the PROPELLING project because we really liked it. And we found a good backdrivability of the system is important. So what you can see here, you see us stumbling, it's actually not that bad how it looks. We agreed on whenever we activate the protective stop and the system stops working, we will stand there for a moment and then activate the exoskeleton again, and we need a small time for rebooting the system. So this is why we always stand there. But actually, if you deactivate the system, you can just walk and go on, and as our exoskeleton is a healthy person, there is no big problem in doing this, and we think good backdrivability is the convenience feature. This is why we made it. But in this test, we figured out, okay, it's actually a very good safety feature. So we had 4 subjects in this test. Was fun to do, and fun is the keyword for the next part, because this is not scientific, but whenever we were done with testing at the hospital, we went outside in Brunette and started doing activities with the exoskeleton. So we went running, riding a bicycle, jumping, we tried driving a car, what actually works, but yeah, we deactivate the system because otherwise it's just full gas or no gas. And this was for us very nice to see, because we were quite happy with the results we made there inside the facility, that we started trying everything we can imagine. We had the system running for, like in the second week, we had it running for 3 hours at once. Like we went, this is from the trip, we went on a bike tour and then started running there, and it was turned on the whole time. We were totally happy with everything we did. So yeah, it was a great time. And I want to tell you about some general findings we had in takeaways. So for our system, we have a very quick adaptation and with little interference. So quick adaptation means if you put on the exoskeleton in the first place, you're clear. Then it takes like 2 to 3 or maybe 5 minutes, and then you figure out how the system reacts to you, and you start changing your behavior in a way that you can support the exoskeleton in supporting you. For example, walking down the stairs, I started changing my gait cycle, and I felt like I will drop into the exoskeleton because I knew it will catch me up, and then I need less energy. And so it's basically you start, so the system of two things, the exoskeleton and the human in our experience will start to change its behavior to get in a more economic state. And this is very quick. There are some tests I know, people on the treadmill, people start like changing their behavior very, very quick. And we had this experience too, and we don't know if it's good or it's bad, but we know it's a quick adaptation, and you can say either it's good or bad. Second thing, on the right side, I tried to visualize it. Our exoskeleton does not improve. So it's for healthy humans, but it does not improve your activity. What it does is it reduces stress and restores capability. So you can do what you can do without, but you can do longer. And the exoskeleton, of course, has a negative effect on everything you do. It keeps you, but not that much. And when the task you do gets sick and stressful, the exoskeleton can help you to reduce this. But yes, without an exoskeleton, you will probably be in normal activities still better than without, for healthy. We found out there are some predictions for useful applications. So in our test, like riding a bicycle, running up and down stairs and everything, we found out for useful application, you need a high range of motion for the movement. That's because when you have small movements, you are probably very economic, and you probably, the exoskeleton has no time to generate force because it's not that, I mean, it's quick, but not that quick. And that's the next thing, the frequency of repetition of movement. So our system at the moment runs on 200 Hertz, which is not very quick for what we did. And we were surprised we can run up to 7 kilometers per hour on a treadmill with a system frequency of 200 Hertz sampling, so it was nice. But again, high frequency movements are normally not that exhausting because you don't have high forces there. And then again, the exoskeleton isn't that useful. Third thing is you need a payload or exhaustion to get the benefit. Because again, humans without an exoskeleton are very economic in their movement. Okay? It's good to have this boundary conditions for further development, especially for what we do, creating an exoskeleton for emergency response forces. It's good to have a clear vision for what is good and what human is better with that. Next, general findings and findings about the test benches. So we heard something about the test benches. For our purposes, we would love to see more challenging tests for this type of exoskeleton, because all our subjects were able to perform everything without the exoskeleton just fine. And so the exoskeleton didn't have to do something to fulfill the task. So it was like the person, the subject, fulfilled the task, and the exoskeleton was kind of co-driver. So this wasn't, for us, was good to know. So this is why we came up with payload, because we thought, okay, we need to, for our use case, to get the more challenging. We found that in everyday activities, I just mentioned it, exoskeletons are kind of inferior to a human without an exoskeleton. But it's like when you're in a good condition, like you could stay in good condition, no payload, no exhaustion, no injury, no disability. And the next thing I already mentioned too, we think in the next years there will be more systems like with this focus what we do, like for healthy humans, for improving some situations, and maybe it would be beneficial to adapt or extend some tests, for example, step-by-step tests, and just adding a defined payload for similar situations. And yeah, what comes next? So we are the PELLEXER project, and the PELLEXER project will put its knowledge in two different ways. So first is in our university, the knowledge will grow. There are other projects coming up, and the development and all the knowledge will be used for different things. And the second thing is called ORCIS, which is the startup company for exoskeletons. And as you can see on the right side, this is like the T3 we call it. This is a more advanced exoskeleton, similar technology, and a lot of findings from our test at the EUROBENCH went into the development, and you can see it already here behind me, because I'm actually right now at the Hannover exhibition called Interschuss, where we present this to firefighters, rescue teams, and to everyone. And we are very happy to have this system here. If you have questions about it, you can ask me. But this is what, like, all the knowledge goes into further development. One side at the university, second side at the ORCIS company, which is actually a spin-off from the university. So ORCIS is still connected with the university, and will continue to work together. So that's basically it. I hope you all heard me well, because there's some background noise. I've activated noise cancelling. I hope it worked well. If you have any questions, feel free to ask. And yes, thanks for having me.
Thank you, Jonas, for this great presentation. I hope you can also hear me still. Yeah? Yes, so we'll go to some questions from the audience. I don't know if there are any questions. None so far. So I have a question for you, Jonas. Maybe there will be a question from the audience later. Very nice presentation. I really like the concept of you saying that, especially for these advanced exoskeletons, and if you use them on able-bodied subjects, that maybe you should have some exhaustion before you can properly assess the added value of these exoskeletons. I think that's a very important message. I was wondering whether you can also relate that message to testing exoskeletons actually with people that have had a stroke or have had an incomplete spinal cord injury, because there we can also sometimes see that difference between the exoskeleton condition and without an exoskeleton conditions, difference might not be as pronounced as you expect. Can we also say that maybe we should exhaust these individuals first as well to properly assess the effects of the exoskeleton?
So we are not experienced with unhealthy subjects, so I'm not an expert in this field, but in my thinking we need some change in condition. So the condition of the person using an exoskeleton, from our perspective, has in some kind to be inferior to a healthy subject. And so if you're healthy in your general condition, you need to be exhausted or have a payload. But if you are, for example, have a stroke, your general abilities are below the abilities of someone who is basically healthy. And there you already have what we need. We need the exhaustion to have an effect. And other people who are disabled, for example, they have already this decrease in capabilities. So I guess, but it's a guess because we don't work at the moment with unhealthy subjects, I guess you can compare our exhaustion to an unhealthy system.
Yeah, thank you for this answer. Maybe it's an interesting topic to also see if this mechanism also works for individuals with some type of disability. There's one question from the audience, Jonas, so we'll wait for this person to get the microphone.
Thank you for the talk.
I guess the microphone is not working at the moment, so I guess you cannot hear this question yet.
No, I didn't do it.
Maybe else you can come. Oh.
Okay. Now, can you hear me now?
Yeah,
so very interesting, your conclusion with the fact that exo for a healthy and so on is not good enough. So I was thinking that you are looking at, and then your answer was about supplementation, and also there is the augmentation application for exoskeleton. Supplementation when you are trying to make a kind of a sub-normal person normal, and then a normal person super normal, if you like. So so maybe the requirements or the benchmarking for these two aspects should be treated differently. So the supplementation and the augmentation.
Yeah, so we at the moment, as we are on the fair, like first time showing a big audience what we do, we get at the moment asked a lot, can you make superhumans? And our answer has to be no. And we always talk about this at the days at the moment. And there is a reason, in our opinion, why it always, not always, from the point of view at our development stages, we need to be, to have the human to be the stronger part. So what we do is we calculate how much force does the person at the moment need, in the knee, to fulfill the task. So let's give it a fictional number. Let's say at the moment it needs 80 Newton meters. And then we say, okay, take 20% of it. And if we go above the point where we take half of the force, the exoskeleton gets stronger than the human. And then it doesn't work because we want to be the one to make the movement. And so we can't at the moment make superhumans. We need this place where the human is weak and needs support. Otherwise, it's going to be complicated.
Okay.
Question, or?
It's kind of, okay, but it's an interesting concept. Which is more powerful, the human or the exoskeleton? This is another topic. Okay.
Thank you.
Thank you.
I guess with this final remark, we have to close this presentation. Thank you again, Jonas, for giving this presentation, and good luck at the location where you're at.
Okay,
thank you.
Thanks. Bye-bye.
And then we're proceeding to the final presentation in this session, combining two sub-projects, the KO and the KOD project, Maurizio Petrarca. The floor is yours.
Thank you very much. Good morning to everyone. Okay. I will explain to you two projects that we submitted to the EUROBENCH that are centered on our adaptive knee orthosis that we tested here in Madrid and in our laboratory in which we extended the BIT scenarios with our technology. I am a physiotherapist with a PhD in engineering, but a physiotherapist, so I will give you a rehabilitative perspective about the use of technology. The first thing that we consider in rehabilitative context is that the minimal unit that we can observe is a subject that is performing a task, like walking, for example, in different contexts, like walking on every terrain on a path in mountain. And during this the execution of the task, you exchange information, geometry, and mechanics that represents the constraints of the movement, that represents aspects that on which you don't need control. And from this aspect, emerge the behavior through a self-organization processes in the organism. Now, rehabilitation is a very, very early discipline. It was born about 50 years ago, and 35 years ago, technology entered in the rehabilitative perspective. Now you know that also me was being young and hairy, and what we learn about the use of technology in our field. The first things that we learn is about biomechanics and physical law that represents a strong constraints field that explain more of the facts of the movement that we are observing. The other aspect that we learn from the use of technology is that when we walk, all the behavior is anticipated. In this graph, the first arrow point the maximum activity of the triceps. The second arrow point at the maximum moment that you can measure at the level of the ankle. The third arrow point at the maximum power exerted at the article. This time series have a lot of explanation that are not simple, but means that the central nervous system needs to activate something in anticipation in order to match the physical interaction of the body with the environment. The other aspect is that a multi-pendulum structure has many counterintuitive behavior that our motor intelligence need to control that are not under the control of our awareness. Another critical aspect is that from a dynamic perspective, we need to control the center of pressure and the orientation of the reaction force vector that push the center of the mass in a very smooth path. In this context, how we can imagine that that the dynamic stability is reached. We know that there are at least three main categories that as anticipatory, predictive, and reactive. They act together. And for recognize them, we need to use specific trials. And also you need to consider that when emerge a pathology, when you have a damage of the central nervous system, you did not have only a lesion of the central system. In the days after the lesion and in the first day after the lesion, change the cord spinal circuits, change the characteristics of the muscle. They change the ability to exert force, they change their mechanical properties, they change their length, change the elastic properties of the muscles and the soft tissue. It means that the central nervous system have completely different resource for managing all the biomechanical aspects that we are facing a very complex challenge. One of the first attempts that we do, we understand that we need to put the patients upright as soon as possible and in the condition to regain some dynamic characteristic. One of the first attempts is conduct using very simple spring that was adapted to the lower limb of the subject and that could work in support the function, and also they was being able to act in some cases as a temporary orthosis that drive the relearning process of dynamic as in that case. This is in contrast with some other devices that have a position control of the gait of the lower limb. For example, in this paper that we published last year, we found that in children with cerebral palsy, this kind of device is not able to produce a modification of the gait pattern in these children. So we are strongly motivated to product some dynamic solution. This is any orthosis in which some elastic component could be tunable, so we can adjust with this orthosis the equilibrium point and the stiffness of the orthosis, and we use it to drive dynamically the reorganization of the gait as in these patients. You can see without the orthosis, and with the orthosis, the very first step. If you look at the second video, you can see that in 3 steps the girl readapt his gait sequence. One month later, he was more able to walk, but the device was able to support the function. In fact, she doubled herself in velocity and smoothness during walking. So the next step was robotization. Robotization was able to allow us to have a phase-dependent control on the function and to exert some perturbation and to study the strategy of reorganization of. Thanks to EUROBENCH project, we updated the first additive orthosis, introducing a spring-damped behavior, because you can consider that muscle are not spring, but they have a like behavior spring. And so this is a language that is very, very familiar for the central nervous system. The other aspect, we introduce in the controller of our orthosis the lambda model, the Feldman lambda model about motor control. That means the organism starts from the initial reference of frame. He programmed the final reference of frame, and he moves towards the final frame of reference, change the lambda, that is the length at which the muscle began to start to exert force. So we introduced this kind of control, and what we obtain is an orthosis that is able, this is a work at 6 kilometers per hour, an orthosis that is able to follow the gait pattern of the subject, but changing a little bit some of these parameters, we observed a change in the frequency or in the knee flexion during swing in the subject. So it is able to interact with the function. We also decided to test an extension of the BIT protocol in our project, because the BIT platform was born in our laboratory, starts from a mechanical solution that we use commonly in rehabilitative context, but we don't have any control on the interaction of the subject between the device, so we need also in that case robotization. It was realized with the collaboration with the University of Sapienza, was mentioned also yesterday. Fabrizio Batanè was being one of the main person involved, and with the collaboration of Alain Berthoz of the College of France in Paris. So you can see control in position and the control in impedance, in which external perturbation and internal produced per the body movement are acting together in order to stimulate the recovery of the subject. We had the necessity to extend this project with a more additive solution. We developed a Stewart platform that have 6 degrees of freedom, and that was able to work in real time with movement analysis system and with virtual reality context in order to have a control also on the vision. Was been before mentioned the fact that movement, standing, reaching, walking are visually guided action, strongly visually guided action. So we developed a new platform. This is the new one. This is the design, and we put the platform at the level terrain in order to use it during walking and during standing on the platform. What we did in extension to the BEAT protocol was being the step on the platform during perturbation using compliant characteristic of the perturbation. It was the first attempt of this girl. Please, you can start the second video in the row. Is it possible to start the second video? Okay, start all. Start all that. If you can see in the upper row is consecutive 3 attempts, and you can observe here in the first attempt an ongoing predictive strategy for recovery the balance, and at the third attempt you can see an adaptive behavior. It was completely anticipated. It was really more elegant. In the lower row, you can see that if we don't give any more a cue to the subject, 1, 2, 3, start, we have again a predictive behavior. She is not able to anticipate. And if we give no instruction, no step, no do anything, etc., you can see that it is possible to compensate this perturbation doing nothing. So we have a very complex system that is depending of intention, of cognition, of instruction, of and we are facing with this complexity. So we tested the ability of our orthesis to follow the subject in this complex task, and we observed that even if different subject, the color is referred to different subject, any subject has its proper strategy, the orthosis adapted to the proper strategy. Also, it's possible to observe the cop that it was maintaining using our orthosis. And the last task was to test the ability of our orthosis in balancing perturbation during gait. And again, here we can have predictive or anticipatory strategy to the platform. In the upper video, you have a predictive strategy, and in the lower, you have the anticipated strategy because he learned what it happens. Also, in that case, our orthosis, there are many parameters that change in this, but we analyze the knee flexion, because when you move in the hole that the platform represents, you need to enhance the knee flexion of both legs in order to guarantee the clearance of the foot from the terrain. And the orthosis was able to follow and also to enhance this characteristic when we introduce some little modification in the control parameters. So all that is a very complex aspect. We have neurological implementation. We have self-organization of human movement. We have biomechanical aspects. We have peripheral aspects that are working. So for that reason, we decided to host in 2023 the International Motor Control Conference in Rome. If you are interested about that, save the data in order to afford in more deep manner all this aspect that I have treated in a very improper manner. So thank you. This is our group. Behind me there is Matteo Bottoni, that is a bioengineer. Susanna Summa is a bioengineer, and Martina Favetta is a physiotherapist. And we also want to thank the EUROBENCH project, because surely one of the merit is also to have give resource to group like us to improve our activities. And I want to thank also Xavier, David, Esperanza that follow us during this year. Thank you.
Thank you very much. Is there any question from the audience? No? Yeah.
Myself, I have a question. So thank you for the nice talk. My question is regarding balance. You said you see the kinematics and analyze the gait with the perturbation. And I wonder if you use some metric to quantify the balance, or you just see the kinematics and analyze that?
No, we are not using specific metrics about that. We are looking at some variables that from the literature seems to be effective, like for example the head behavior, because inform us the use of the gaze. Also in the previous presentation this morning was evidenced that the role of the vision in the control the balance. It's known, for example, that if you give the instruction to look at a fixed point in front of you, you can conduct any perturbation of the balance under you, and you are able to adapt to any perturbation, anchoring your body configuration to the visual field. So we are putting attention from what is known from literature on motor control to some peculiar variables like that are effective. The other, when you're walking, is the clearance of the foot, for example. So the clearance that you reach when you have a perturbation is another aspect that is really important, and you can understand if this clearance is obtained through a pelvic strategy or a knee strategy. And this informs you how the system have the real unknown aspect about that is perception, because we know a lot about movement, but perception and the strategy of sensory integration are peculiar of each single subject, like the strategy of movement. But these are interior processes that was difficult to understand. This is one of the reasons because we are using, for example, virtual reality in order to control vision and to create some disgregation of between information and have some insight also about that. I don't know if I...
Yes, sure. Thank you.
Diego, we have still time for more questions, yes? Yes, one. Yeah. Do you want to...
Thank you so much for your presentation. Very interesting to also see the effect of a disturbance on how an orthosis works. I was wondering whether you also studied different kind of perturbations, because in the video we saw up-down perturbations, during walking, I mean. Did you also look at tilted perturbation? And what's your experience, what people find the most difficult perturbation to deal with?
The lateral perturbation is more challenging. Now we are studying more the zeta, the vertical perturbation, also because in many pathologic conditions people walk on toe. So we need to understand what it means for them and how we can modulate this behavior. But it is known, for example, that hemiplegic patients have a great lateral instability, and they use the shank muscle to control. And this is one of the future for the young people of the laboratory. We are leaving a great job for them.
Thank you very much.
Thank you very much to Maurizio and all the speakers and the chairs. And now we have this. Yeah, you can go. Thank you. We have now the institutional closing, but we are waiting for this representative. She is not arrived yet. No? So maybe what we can do is to. What's the estimation of time we have? So just for me to decide what to do, even dance or sing. We don't know. Just 1 second. Okay, all this was on purpose because now there is a surprise part, which is the poster award ceremony. It was at 12:32. So, waiting for the presentation. So it's really nice to have all these posters actually. So this the number of posters, I think it's was quite high with almost 20 posters. I have to thank the scientific committee also so the bad guys that were around yesterday, so they have had hard work to evaluate all these posters, so they enjoyed all of them actually. Actually, they was pretty difficult to define because they were not in total agreement, so we had to find out. So thank you very much for your participation. It was really difficult to put all the talks together because we have 59 consortia, so it was you could fill 1 week of presentations, no? But with this poster we could fill it. No? So these were the posters participating. One thing is, when you leave, if you want to leave your poster here, we are happy because we can put somehow to show also in the future what's around this facility. So, but please feel free if you need to bring this to take this with to your lab. It's okay, no? Okay. So about of these 17 posters, we selected 3 finalists that I will kindly ask you to come here. And these are the 3 finalists. So the first one is about the BIS table with the poster titled Balance Assessment Using Visually Cued Gait Adaptation. Please come here to make a bit of suspense. And the second one is about the Rekine. It's Rekine reconstruction kinematic trajectory during walking from EEG signals. Maria. And the third one is functional ergonomic and neuromuscular assessment of twin-act exoskeleton in healthy subjects and post-stroke subjects. Okay, so these posters are about one on a FSTP1 project. So they make the protocol. Now you've seen also a presentation about this. Then 3 actually FSTP2 projects. So Rekine was one of these, and then Fit and Fit Stroke are the same group that want to one coming to the facility and the other one staying in your lab. Okay. We have half an hour, so we can wait a bit more. Okay. So, which are the winners? Do you think? First, the second, or the third? This one. So, thank you very much. So this work was really very well explained. They tried this two-in-acta robot developed by IIT and then Fondazione Carlo Gnocchi and Consiglio Nazionale Ricerca CNR of Italy. They did this combined project. We're seeing actually the two-in-acta. It's a very nice exoskeleton we tried here. We tested it on the step-by-step and other situations, and also they've done this with stroke patients in their own lab. So really congratulations for this. And okay, so now the wonderful prize for this is, since you have a lot of people, we cannot spend so much money, so you have wonderful cups, EUROBENCH cups that you have also for all your friends, all the authours. I think you need another luggage to go back with this. So, and for all the finalists, you will be invited to submit a paper on this. So if you are preparing this, so you are, say, you will be having a special treatment, say, during the special issue. Still deciding which journal, because we were thinking about Robotics and Automation magazine as a first choice. But some of the work are really human, so application on humans. So maybe we can go more on more human neuroscience journal. So we are dealing with some journal, and this is also a message for you. So if you are, some of you are preparing some publication. So if you haven't decided yet the journal, maybe wait a couple of weeks until we tell you which is the special issue which is focused on EUROBENCH. So if you have some patient, so could be nice also to show that we are a community that and we have good scientific content. Okay, so thank you very much for all your participation, for the finalists, and and I have the word. So. I have wonderful diplomas here, wonderful for the finalists. Thank you. Come here and can you put the slide again, please? So we can make a photo with the finalist here, and maybe someone can take a photo. I don't know, we don't have the photographer is not here, no? Okay, but yes, in any mobile phone, it's okay. Can you put the slide, the presentation again, please? So we can have here, yes? Here, okay, so you can come here and... Okay, thank you very much. No, take your cups. Okay, so now we have only 22 minutes more to stay together, and let's make some improvisation. And I would say we can make a small round table, because this is something that I had in mind to make, and we didn't have actually time to do this. But I think that this is something that is really useful. So I would like to invite some person here. Okay, so first the Scientific Advisory Board. Gurvidin, Jan, Reinhard, please have a seat. Then who else I would pick? And maybe some also for Anthony. Come here, please. Okay, I think with 4 people is okay. Then any other can, of course, intervene. So I would like to talk about the future. We have seen what we all have done in terms of hardware and studies. No, I've talked at the beginning about which could be the future directions. Okay, in which we can, of course, apply for projects together or part of us. It will be difficult to have exactly the same EUROBENCH approach in a future call, because now we have a benchmarking framework. Maybe it's not at very high TRL, but we verified technically that the framework is working. No? So my question would be now, how do you envisage it, like the future? No? Which are the possible new direction for this? What's the next step or the next steps? Any consideration? Yeah.
Yeah, I think you built very nice facilities. So that's of course a very good starting point. But I also think there's a big difference to pay researchers to come here and do an experiment, or to let people do that on their own, or even make them pay to use such a service. So I think there is a gap that you have to cover, and I think the first step is typically to, in the context of other European projects, we have now a big community of people that know what is happening, and they should also think about that if they make a new proposal, that they also think, can we somehow do an objective benchmarking test of the results? So can we use this facility and maybe also reserve some funding in your proposal to do a benchmarking test of your research result, and not only do that in your own lab, but say this is an independent facility where we can do that according to defined protocols, and also in that way support to further extend it. So I think that's very important. Could be that you are a member of the consortium, but it can also be like a subcontract or a service that you plan in your project proposal. So I think it's very important that everyone that now has seen this and used it also thinks about it in their future projects, like can we somehow use it? And also Europe has their facilities called digital innovation hubs that are also meant to provide supportive services. I think that could also be a way to somehow connect to a digital innovation hubs and integrate it as an innovation service to do benchmarking. So that would be my first bit European project-oriented comment. Of course, there's also the way that once you have standardized tests that companies have to do to demonstrate their product safety or performance, then of course companies are very willing to find a facility where they can do this test. But I think usually companies will do what they need to do. Or there's maybe an agreement. Also in the car industry, I think there are kind of agreed tests that people do just to demonstrate. But somehow there needs to be some pressure, because I think companies, of course there can be a benefit to compare, but there's also always a risk to compare and to have an objective measure. So yeah, this would be my starting comments, but not sure I can pass the mic to someone else. Or maybe in the audience, but...
Yeah. I'm not sure if you're ready for this, but we spend a lot of taxpayers' money on this. We reached some really good results, but I think now, or maybe in a few whatever time units, it's time for us to give something back something more than just playing with some patients for a test, but to do something real. So my expectation would be that we turn these really great research results into something useful for society, and if we want to exaggerate, for mankind, possibly. And I would like to support this movement, this motion. It may not be successful for all the cases, but I've seen some really great results here, and some of them should turn into something really, really useful, really great, and really to continue in the future. So if you feel like it, please don't hold back, huh? Research is not research for itself. Research is for society.
Thank you, Reda. Thank you. Anthony, you want to comment something on data aspect, or software aspect, without any insults?
So on the software aspect, I mean, it was quite a journey, and I think the journey is not finished. And it should not, because otherwise it will be a failure, because, I mean, quite a lot of effort has been spent on that, and I think we have to continue that effort. I think that 80% or 90% of the metrics code is publicly available, which is great because other people can just reuse it, and I think it's good to continue this effort, even if there might be some delay to enable publication. But I think it's good to share material, to share this simulated environment also to validate humanoid system. So I think we have to continue and also improve the mechanism that enables to reproduce experimentation, because that's also what will enable to continue improving the comparison of systems, the benchmarking, and hopefully, I hope we can also maintain this and really use this database, which was not yet really used. But I think as usual, I have the impression that when we finish European project, that's the moment where we should start it again. So I hope we can keep this synergy, and because there are some great opportunities, I do believe.
Yeah, actually, in this respect, we found out that the protocols that we propose, some of them were used as is, but many of you asked us to modify something. No? So we figured out that it is really difficult to find one protocol that fits all. No? But in terms of then comparability, we need to have a protocol that fits all, because otherwise you always stay in different areas and you cannot really match. No? So we sent you a question actually yesterday, because it's very important for us to know your perception on this, no? To find out whether we can converge in some cases, or we have to diverge in the sense that we have to make two different protocols, because these are two different aspects. No? So that iterative process, I would say no one has done it before. No. Everyone is selling the standardization, the comparability, but then no one entered. So we are the first that really entered this. So, and we are discovering, which are the possibilities.
I would also like to add something to this, because I think it's great achievement, and we have a community of researchers here, but it's not a community that keeps meeting up together. So I think it's also really important to try and connect to a network or a community that can maintain this and extend it. And I was thinking, for example, the ICOR, Rehabilitation Robotics, is not only a conference, but also has now a society, where also I think people here are member of. But it's difficult to find one focus, because there's also industrial exoskeletons, which is again very different from rehabilitation. But I think it would really be important to link it. Could also be an IEEE technical committee, but something that will remain over the years, that can somehow take it over. Because if you depend on a group of people that now meets, but then doesn't have any funding to meet again, it's very difficult to keep it alive, I would say. And the cost action could also be a solution, but also that's temporal. So it could also be a more established society of
Yes. Now what we are working is to, together with Fabio Bonsignorio, we are leading the topic group in Europe.
That's one channel, but I think they are not really very well connected to the research world.
And they're not funded.
And not funded, no, and that's a big gap. So I would really think also about this other
network.
type of more self-funded groups. Yeah. Maybe someone has ideas also.
I would just like to start right away. We do have this web page as an entry point, and I've seen so many European projects where the web page got offline the day after the funding was over, and some even turned into some very bad web pages. So after some time you tried to refer to it, and then you didn't want your wife to see. So please consider keeping this web page alive and maybe inhabiting this with the results we've seen here, with the posters, maybe with some links to the work groups, with some data. Actually yesterday, I'm sorry I forgot, but there was this one interesting project. I wanted to send an email to my student, have a look at this, but I couldn't find anything recently, and so that's a real pity. Please, even if you have to pay this 10 euros a year for a web page, please do.
We'll see how much money is left.
Well, is there somebody with a hat? We do collect the money for Diego to keep the web page alive.
We'll pass with a cup, a EUROBENCH cup.
It's free on GitHub.
Okay. Yeah. We are also using GitHub, of course. And maybe Gurvinek, you want to comment something on standardization, because Gurvinek is a worldwide recognized expert in standardization. He's been a convener in several technical committees, and one of these in the technical committees 299 on robotics, and he knows very well how this goes. No, my question for you would be. How far are we, or how long would be the path from having this and then converting this into standards, standard test methods?
Well, they're coming. I would like the research community to be a little bit more focused on safety, as I've said a few times. We as researchers tend to be focused on performance. My algorithm is better than your algorithm and so on, which is fine, but from commercialization and from regulation, standardization, you go to the ISO, IEC, the only thing they're interested in is safety, really. So we researchers tend to focus on putting functionalities which actually compromise safety, like AI, machine learning. These are all actually liabilities from safety perspective. So if you want to give your exoskeleton or your humanoid or something the ability to self-learn, you can imagine that the certification that you have worked on, as soon as you press the self-learn, you lose certification, because the algorithm, the robot is now different. It has changed. So so in many cases, thankfully, when you're dealing with machines, you can self-certify. This is the advantage. For medical, you cannot self-certify. You have to, and when you have to do clinical, it's a lot of money. You have to spend a lot of money. And so making commercialization of medical things is very, very expensive, not only just to achieve the registration and the safety certification and so on. The IAC, the 60601 family of standards, is now thinking about the 4th edition. I'm involved in that 4th edition planning, where something like 100 standards are being merged into, well, much fewer. So because these 100 standards, they're all published at different times, and if you refer to a standard, some standards change, and so it really is a very complicated situation. And many countries have adopted different versions of these standards also. So if you make a medical exoskeletons, many of you have been talking about that. Maybe if you go into Germany, they will have different regulation than when you go to UK or to go to US or Japan and so on. So the regulations are very, very, very complicated. But we as researchers, I think, do need to understand the process. We really do, and I think that if benchmarking, Euro benchmarking is to continue, I would really urge safety to be the driver. Because otherwise, you will keep the rift between the research community and the industrial commercialization, the companies. And I believe these two communities must be brought together. And the only way is to make sure that they have this common focus. And the common focus is safety. And there's no ifs and buts about it, because that is the only driver. And I know many of us, Reinhard, we have been promising this delivery of robots since the late 90s, some of us. And we have a lot of young people who are promising the same thing. You know, and really the European Commission is kind of used to hearing these promises and no delivery. Yeah. So it's important for you to know that, you know, I don't know if you have heard the word standing on the shoulder of giants. Do you understand that? Yeah. So please look at those giants and try to stand on their shoulders, not just on the ground and say, what the hell are these guys have done? Because they've done something, and try to see the horizon from those shoulders. So thank you.
Thank you, Gurvinder. Maybe the last comment from Jan, and then...
Okay, yeah, because I agree mostly with Gurvinder, but I would also like to add something to that, because you're completely right that safety is the baseline. So if you cannot deliver a safe system, but I know, especially in industrial exoskeletons, at this point, also an American standardization, the ASTM group, is working on a lot of standards for industrial exoskeletons or wearable robots, very much in line with what you're doing in EUROBENCH. So also saying, how should you do a usability study in an industrial environment? How should you walk on difficult terrain? What kind of tests do you want to do? And actually, because ergonomic exoskeletons are a reality now, now companies ask, like, what's the difference? What do I need in my situation? So that there's really a need, concrete need from companies to select exoskeletons, and that drives very much this kind of standards. So yes, safety is key, and especially in medical safety is really the key thing, but companies also want to buy and select products, and there's also work done, and I think you could connect to that also. If you work to links to that.
When you're dealing with machinery, you deal with something called safety, right? When you're dealing with medical, there's two things. You deal with basic safety, which is more or less for machines, but there's something called essential performance. Has anybody heard of that?
I don't think so.
Thank you. Essential performance for a medical device, this is all to do with single fault condition. So when you develop or design a machine, this thing has to make sure it doesn't cause harm under a single fault condition. Okay? So you have to look at your system. Where can it fail? And how does that failure impact on the safety of my system? So you have to go through all the permutations of your system, the failures. Now, in a medical device, you have to do that, but you have to now talk about my medical device has an essential performance. I'm going to resuscitate a patient, okay? That is, for example, or for an exoskeleton, I have to maintain balance, for example, okay? Now, what a medical exoskeleton will then have to do, it has to, under a single fault condition, make sure it maintains the essential performance as well. Can you see the difference? So it's not only the basic safety, i.e. not cause harm, but make sure it maintains the essential performance that you claim is the point of your medical device. So if you say stability, it has to maintain stability of the patient under single fault condition. That's the challenge. Can you see the difference?
Yeah. We can see. Actually, I think these comments. Now I have to close. Sorry, but this comment is very rare because normally research people don't look at this. They don't know anything of this.
Essential performance is very important for medical devices.
Yeah, we have some couple of minutes more.
Well, just 2 comments. I'm from circuit design, so we have some requirements, 99.9% fault detection rate. Otherwise, because if you have 10 million of transistors, if a single one fails, the entire thing is gone, and you need to find this out. So it's pretty much the same, and you can have a look into the research in this domain. Another point which hasn't been mentioned yet is the cost. So too many researchers completely neglect the idea of that the devices have to be paid. So if you sell a single exoskeleton for 100,000 euros, that's not a big deal. But if you want to sell, let's say, 1,000 of these, it makes a big difference because somebody has to work for it, somebody has to pay for it. So too many researchers kind of forget about this costs that can be incurred by the technology. And too many, well, those who think about cost, they think, well, maybe in 10 years there will be some process to make things cheaper. This, however, is too late. So maybe you want to think about this.
Yeah, in this respect, maybe also having a testing methodology can help you to define, okay, what if I change the actuator or the structure? So is this maintain this performance level, or how much is decreased? No, that could be also a useful tool for that. Okay, I think we have to stop. Yes, thank you very much for the roundtable, for your adaptability to this. Thank you. So I think that due to this delay, probably caused by the traffic, no? Traffic jam? Okay, so 1 minute. And we have to maybe delay also the lunch, half an hour, I suppose. Okay.
The bus.
Eh?
The bus.
And the bus, we have to tell the bus drivers to stay calm.
Anyone with a robot to do some magic tricks or some entertainment? No, so you have to do it.
Yeah. Okay, there will be 3 people. There will be the director of the hospital as yesterday, Dr. Alemani, and there will be Jesus Tornero also, that wants to say a word about this event and close institutionally this event. And then there will be the director of research and innovation technology of the Community of Madrid, which is the person that now is coming. Just a bit patient. They are there. now we're going to switch to Spanish to make this institutional closing. So, gracias a todos los asistentes y gracias a doctor Antonio Alemani, a Jesús Tornero, a la ilustrísima señora doña Ana Isabel Cremades. Vamos a empezar con unas palabras por el doctor Antonio Alemani, director médico del Hospital Los Madroños.
Buenas tardes, todavía no son buenos días, buenas tardes. Directora General de Innovación e Investigación Tecnológica, doña Isabel Cremades, muchas gracias por venir. Director de Investigación, Desarrollo e Innovación del Hospital Los Madroños y director del Centro de Neurociencias del Hospital Los Madroños, don Jesús Tornero, muchas gracias por estar con nosotros. Diego Tricelli, director de EUROBENCH. Buenas tardes a todos. Vamos a celebrar dos jornadas que han sido súper intensas. Dos jornadas que hemos llegado a tener, a adquirir mucho conocimiento y hemos ayudado a intercambiar conocimientos. Han sido 24 comunicaciones y 21 póster de 80 empresas, universidades y centros de investigación. Reunir en 2 días tanta sabiduría y tanta ciencia, pues no es fácil, ¿no? De tal manera que muchísimas gracias a todos los que habéis aportado vuestro conocimiento y que lo habéis puesto en común con los demás. Es muy importante para un hospital el tener este nivel de conocimiento a la mano, ¿no? En estos 2 días oía yo a Jesús Tornero cuando estaba presentando y bueno, el laboratorio abajo, y lo he oído varias veces decir, bueno, el centro de todo esto es el paciente. Y no puede ser de otra manera. En ciencias de la salud, cuando nos hacemos una pregunta que va a desarrollar un proyecto de investigación, lo tenemos que hacer siempre pensando en el beneficio del paciente. Siempre. Porque si no, estaremos equivocando la pregunta. Será para investigar en otras cosas. Pero en ciencias de la salud, si no pensamos continuamente en que el paciente va a ser el destinatario de lo que vamos a investigar, pues hemos hablado. Y yo sé que en estas 2 jornadas el paciente ha estado presente. Y todo lo que habéis portado es para el beneficio del paciente. De tal manera que el Hospital de Los Madroños no puede hacer otra cosa que agradeceros todo esto que habéis plasmado. Porque es la manera de mejorar el estado de salud, los cuidados y la forma de rehabilitar a los pacientes. Por lo tanto, responder de alguna manera la confianza que nuestros pacientes ponen en nosotros. Y lo que piensan y lo que esperan nuestros pacientes de nosotros es que sigamos siendo líderes en la neurorehabilitación. Y estas jornadas ayudan a que el liderazgo del Hospital Los Madroños en su neurorehabilitación siga siendo puntero. De tal manera que muchísimas gracias. La unidad de neurorehabilitación del Hospital Los Madroños tiene una peculiaridad, podríamos decir, que le da valor añadido. Y es que está en el entorno y en el seno de un hospital médico-quirúrgico. Eso produce seguridad en los pacientes y seguridad en los profesionales, en los fisioterapeutas, en los rehabilitadores, que saben que tienen amparo ante cualquier contingencia de un hospital médico-quirúrgico, de la potencialidad y de la complementariedad que tiene el Hospital Los Madroños. Yo quería agradecer a la Directora General de Innovación e Investigación Tecnológica su visita aquí hoy para el cierre. Le puedo asegurar, directora, que va a celebrar unas jornadas que han sido muy importantes para el Hospital Los Madroños, muy importantes para la Comunidad de Madrid, y que esperemos que sea pues un inicio para nuevos EUROBENCH, si es posible, pero estaríamos gustosísimos de que haya nuevas iniciativas de investigación. Muchísimas gracias.
Muchas gracias, doctor Alemani. Vamos a dar la palabra ahora a Jesús Tornero, director de I+D+I del Hospital Los Madroños y también director del Center for Clinical and Neuroscience.
Bueno, muchas gracias a todos. Yo voy a ser breve porque después de los discursos del doctor Alemani es difficult to, I will change to English if you want. It's difficult to improve your speech because Dr. Alemani is well known and with highly experienced in speech. Bueno, Yo realmente lo que quiero es agradecer primero a Diego Torricelli como coordinador del proyecto, a todo el grupo del Instituto Cajal que han hecho un trabajo increíble durante todos estos años del EUROBENCH. Me gustaría agradecer al consorcio todo el esfuerzo, a las FSTP1, a todos los proyectos de las FSTP2 que han ido viniendo aquí durante los últimos meses. Un especial reconocimiento a INCOM, que hace una labor, bueno, no siempre tan visible, pero que es fundamental en un proyecto europeo. Me gustaría, por supuesto, agradecer a todo el personal del Hospital Los Madroños que han participado en un proyecto europeo de alguna manera sin ser un centro inicialmente de investigación y muchas veces no se... Es decir, los proyectos de investigación tienen sus particularidades y realmente no siempre no estábamos acostumbrados, ¿no? También un especial reconocimiento a la gente de los empleados y la gente de biosensores y colaboradores. Biosensores Inteligentes para la Salud es un spin tecnológico del Hospital Los Madroños, cuya marca es Integra y que hace también un papel pues no siempre valorado porque hacen muchas veces de soporte. Y, por supuesto, quería agradecer a Ana Cremades, a la directora general de Investigación e Innovación Tecnológica de la Comunidad de Madrid, por su cercanía, por entender que el campo en el que estamos trabajando, la neuromecánica, exoesqueletos y tal, es un campo muy importante y por tenerla aquí, que es un lujo. Nada, no me quiero extender mucho más. Muchas gracias por todo y ojalá que todo lo que es la estandarización y el benchmarking pueda ser en el futuro un estándar y dentro de unos años lo veamos no como investigadores, sino lo veamos como en manuales de calidad de todos estos sistemas de neurorehabilitación. Muchas gracias por todo y hasta siempre.
Muchas gracias, doctor Tornero. Y ahora damos la palabra a la ilustrísima señora doña Ana Isabel Cremades, directora general de Investigación e Innovación Tecnológica de la Comunidad de Madrid.
Pues muchas gracias, muy buenos días a todos. Sobre todo, pues muchas gracias por haber contado con nosotros y con la Dirección General para cerrar este evento. A los organizadores, por supuesto, doctor Alemani, doctor Tornero y a todos los participantes, ¿no? I would like to tell you that you are in a center, which is a new one, but that will become very fast in a reference center for our community. I think that this initiative of the EUROBENCH project is very much appreciated for all you, but it will become a reference one for the business and the companies that want to start with this kind of robotics and prosthetics and so on. That is very I think that we have a need in our society now and in the health industry and the technological solutions for health, and this can become a really very important business area and sector. So this project is aimed to create the first benchmarking framework for robotics systems in Europe, and this will allow the companies and the researchers to test the performance of different exoskeletons, humanoids and other kind of devices. And in this case, you are very much focused on this bipedal locomotion, but I think that maybe in a future this can be even explore another kind of solutions and applications as well. So this goal is well aligned with the competences of the Directorate General for Research and Innovation Technology. And we promote too the cooperation between the university, the science and the industry to contribute to the development of innovative but always knowledge-based, efficient regional solutions for not only for our society in Madrid, because nowadays all the challenges are global, and that's the point that Madrid wants to contribute to the global system and not only in a local way. So the regional government of Madrid is working to promote Madrid as a friendly region and a preferential place to start university studies, research projects, and business initiatives with the best conditions, providing multiple networking opportunities, as well as a very relevant, talented region with many people that can contribute to your projects. So thank you very much for having this workshop or conference these 2 days that's in Madrid and in Brunete, in Hospital Los Madroños. Everything around robotics and robotics applied to the health area is a strategic goal for our community. In Madrid, the robotics sector is quite relevant, and it is growing to accomplish the present and future needs of different application fields. And the research and industrial developments are the foundations to build on. In education and science, we understand quite well the value of cooperation and collaboration, seeking for alliances and partnerships. And this summit has been, I think, the best opportunity to develop your ideas and sharing your experiences, your best practices, and providing a solid network. I hope that you have here these 2 days the best experience of Madrid, the best experience of Hospital Los Madroños and the whole team of the project. And I hope I can see you in the future in Madrid again. So thank you very much.
Thank you very much for this wonderful closing, all these kind words. We try to accomplish all this. So now we close and we can go to lunch. I think it's wise to postpone all the program 30 minutes. So I would propose to start with the plenary talk from Nicola Vitiello at 3:30. So we have more time to go to the buses. Okay. So also for the people that are listening us through streaming, please connect again here at 3:30. Thank you very much.
Okay, so we are here with just 10 minutes in advance with respect to the delayed time, so I think we can start. So I have 10 minutes to present and to introduce you to Nicola. So Nicola Vitiello, a big pleasure to have Nicola here actually, because we have been talking about this several times before the project, and then he also is, so he's from the Scuola Sant'Anna di Pisa. He's professor of biorobotics, and he's the director of Wearable Robotics Laboratory. He's a biomedical engineer with specialty and PhD in robotics, and has been professor during, and is still a professor, but he also is one of the very few people that achieved to start with a spin-off company in robotics. Very soon it's been acquired by bigger companies, and with a very advanced prototype that's been converted or is about to be converted in a promising commercial product. So I decided to invite him because he's a person that knows all the range from lab to the market. So for us, as we have seen also in the round table, we as researchers, we always miss this last part that seems very a small step, but it's actually a very big one. So Nicola is on one side a researcher with a big group of researchers, but also he runs this company. So he has these two very valuable sides. So I'm very happy to have you, Nicola.
So, good afternoon. Thanks a lot, Diego, for this nice introduction. It's really a great pleasure to be here after 2.5 years without traveling abroad. So I feel also a little bit strange as I say it with some of you. So I was thinking a lot and devoting attention to prepare this talk and trying to understand on what focus the presentation. And in the end, I said, okay, even if EUROBENCH is about lower limb, I want to talk about upper limb. And the reason why is that the upper limb exoskeleton is where we managed to go from lab to market, while on the lower limb, we are still working on developing products. So, I mean, the parabola is not yet complete. But you will realize that also in this case, even if there are products on the market, the parabola is not yet complete. So as Diego said, and as my rector suggests, I have to disclaim that I'm co-founder, director, and advisor of a spin-off company of Scuola Sant'Anna that is called UBO, which, by the way, does not any relation with the Juventus, because as many of you know, I am a big supporter of Napoli, just to make it clear, okay? So, introduction is mostly about the motivation of our work. I think that we all know about aging of the population and what are the implications, but I think that this is something that we should push more and more on, because actually the COVID, the pandemic, just alerted everybody that the sustainability of our welfare is not there, and technology can be really one of the solutions. So I don't want to go through the statistics, but maybe in particular younger researchers have to consider that this is not just something that we go around and say, look, we work in aging, technologies for aging. This is a real need, okay, and the market is there. Of course, doing exoskeletons is something that we know it's challenging. In our laboratory, we have experience on human-robot symbiosis, physical human-robot interface, on kinematics, how to deal with mass distribution, tailoring, which is very important, and also on cognitive human-robot interface, on how to get intention, and how also to detect spasticity. But, of course, today, you will see how those things have been somehow implemented or researched in the case of upper limb exoskeleton. Before I go ahead, I want to share with you the rationale of this presentation. I want to first share with you what we did in the last almost 15 years. It is not a long story, you can trust me, about research activities in the academia, and then how the know-how matured was used to develop a product in a completely different sector. So my career started with this device, the NeuroExos elbow module, that was an elbow exoskeleton, almost 15 or 16 years old, that was developed to mobilize the elbow with the aim of treat spasticity or treat the elbow to prevent spasticity from raising, so minimize the risk and the occurrence of spasticity. And of course, also to try to collect objective data on the state of the patient. The device was done in several versions. The one that you see here is the one that we still use in hospital for research activities. Is a full powered elbow exoskeleton with passive degrees of freedom to allow human-robot joint axis alignment, and capable of both robot and patient-in-charge control modalities. The first study that we did was with post-stroke subjects. We mostly involved 17 stroke patients, and the test was mainly aiming at verifying the usability of the device. And this was also my first experience with certifying robots for clinical investigation. Now the device is adopted in a randomized control trial, which is still ongoing in the Versilia Hospital with Professor Federico Posteraro. And this is a randomized control trial where we are essentially comparing conventional therapy with conventional plus robotic therapy in mitigating the risk of spasticity at the elbow level. The methodology has been published in Frontiers Neurology with the aim that other colleagues around the world can take the same protocol and maybe collecting similar data so we can collect more evidence. Here there should be two videos just showing patient with higher and lower Fugl-Meyer scale, because in this case, I don't know why they are not, maybe I ask the colleagues if they can just play the video, but it's not that much critical. But you see on the left side, patients that are not capable of moving, it's the robot doing the job with the robot in charge task. On the right side, we have the patient doing the task. And we, in the case of voluntary activities, also record EMG activities. Our dream is to correlate outcome from functional assessment by therapist with the data from the robot, which is a kind of old dream for wearable robotics and rehabilitation robotics, more generally speaking. After the elbow, we moved to the NESM device, which came in 3 different generations. So with the NESM NeuroExos shoulder elbow module, we tried to learn, to take advantage of what we learned with the elbow to also the shoulder joint. And we essentially tried to develop a upper limb exoskeleton for elbow flexion extension, shoulder flexion extension, abduction, adduction, and intra-axial rotation. So the alpha module was developed almost 7 years ago, so this is quite old research activity. We, in analogy to the elbow exoskeleton, we used the series elastic actuators, and we tried to develop also passive degrees of freedom to align the robot and the human rotation axis. The 3 axes of the shoulders are the one that, I don't know if there is a laser here, maybe yes, but yeah, are these 3 axes here. And then there is the elbow joint, which is similar to the previous exoskeleton. We paid attention to follow the vertical displacement of the shoulder articulation in the frontal plane and the horizontal displacement of the shoulder on the horizontal plane, essentially following the glenohumeral joint. With the beta version, we followed two lines of improvements. But actually, I like to say that this version of the device was a big failure. So this device was not that much performing. But we, for the first time, explored the use of series elasticity with an hollow shaft, at least the first time for our lab. And we tried to have the same device flippable for right and left side use, and also integrable in a wheelchair. This happened within a European project called AIDE, together with Nicolas Garcia in Miguel Hernández University. The control architecture of all the elbow and NESM alpha and beta is the one that you see here. So in the robot in charge, there is an high-level control that just plans the trajectory, the joint trajectory, while patient in charge, there are different modes of interacting with convergent, divergent, auxotonic, isometric, and isotonic mode. Nothing new. This device, so both the NeuroExos NESM alpha and beta have been used in some experiments. I like to mention that this device was used in the AIDE project for testing interfaces based on gaze, or EEG and EOG. And in particular, this experiment that we did together with the colleagues in University of Miguel Hernández University and in University of Campus Biomedico in Rome, we essentially, and in Tübingen, we developed an interface based on EEG and EOG to control simple tasks like grasping an object and drink. The interface was tested with healthy individuals, and result showed that the time to initialize the execution of each subtask is below 3 seconds, and the reliability, so time to successfully initialize 75% of the subtasks, was under 5 seconds. This result was interesting for us because our goal is also to use these devices for neurorehabilitation. And so our dream is to have biosignal triggered upper limb movement. In the Cedar Foundation in Northern Ireland, we have tested and benchmarked the exoskeleton with a robotic arm with tetraplegic patients. The data have been collected and will be published soon, and results were quite interesting. This is just to say that even if we collected data a couple of years ago, we are still analyzing data about this use of the technology with tetraplegic patients. More recently, we have delivered a new version of the upper limb exoskeleton, and a paper that has just been accepted on Robotics and Automation Letter, where we present a new version of the series elastic actuator that is used in this 3rd generation, and a new kinematic structure where we essentially have deployed the passive degrees of freedom in a different way. Now there is a video where this is showed. Hopefully you can see the level of fluency that we have with our upper limb exoskeleton, which is fully powered. This is the transparent mode, and by combining the passive degrees of freedom in the shoulder and the intra-extra rotation at the shoulder level, we managed to have a quite fluid movement for, this is the PhD student that works on the platform, but I can tell you that I also have tested myself, and I was really impressed by the level of transparency and the compensation of the inertia term that we are able to achieve, and gravity. And so of course, we do not expect that this is a product, of course, but what has been achieved in terms of performance are a good basis for developing future product in the medical sector out of this technology. This last version of the device has been developed within the European project REHYBE, where there are several partners. The project is coordinated by colleagues in Technician University at Munich. And this device is also one of the first, one of the few available in literature that in relatively 1 minute, in about 1 minute, you can flip from right side to the left side. So at least in case of of use in clinic or hopefully also at home. With the same technology, you can maybe address right and the left-sided impaired people. So, all this story to say what? To say that for about 15 years we have worked on exoskeletons for upper limb. And of course, our dream, the dream of my collaborators, is that we would like to bring those technologies in the market. But in parallel to this, there was another story that started on 2015, and then you realize that thanks to the knowledge we matured in the field of rehabilitation robotics, we could develop a product which is completely different sector, which is the story of what we call MATE or MATE-XT technology. The story is about EUVO, which is this company that, together with some other colleagues, we raised on 2015, so it's almost 7 years ago. And starting from 2017, we were acquired by a joint venture between Comau and Ossur. With which goal? The goal was to develop wearable robots for market, with a business model which, in my view, is a little bit new with respect to the technology transfer activities that we are used to, at least in Europe, which is the one that we call of open innovation or industrial coaching. So essentially, EUVO is not directly interested in selling product. So we develop products for our shareholders, Comau in the industrial market and Ossur in the medical market. And for partners, so for ourselves in the consumer fitness market, which are the three lines of business of EUVO. By the way, there are colleagues in other companies, like Ottobock is one of these, or Sweetix, or that now, I mean, many other companies are showing interest in industrial, medical, and consumer fitness market. So maybe there is something of value in organizing the business according to these three lines. Of course, we are also engaged in European projects, but they are not really our big part of the story. What is happening here? So the team is about 15 engineers plus 3 that will be hired in the next 1 month. There is 1 CTO and 2 admin staff. So in total there are 21 people hired by the end of June. And we have 1 CEO that is a manager in Comau, and of course my role in the company is mostly advisor for business development. And the challenge that we faced first is the one of developing exoskeletons for industrial market. So Comau and Ossur came to us, proposed several challenges. Comau in particular said, look, we want to develop an exoskeleton for workers because we want to relieve workers from fatigue, which is a nice idea for a biomedical engineer. I mean, we don't like fatigue, so why people should be strained by working conditions that are tough. And of course, we were not the only ones. In the state of the art, there is an increasing amount of colleagues around the world that are going to develop and that are developing exoskeletons for workers. Of course, I'm not the one that pretended that what we do is best. Of course, we just like the idea that there are competitors, because I mean, if there is no competition, there is no market, and if there is no competition, there is no EUROBENCH facility, by the way. So we are in the line of passive exoskeletons. So we wanted to develop our own passive exoskeletons for upper limb, and together with colleagues in Fiat Chrysler Automobile Group, since Comau was part of the FCA group, now is part of the Stellantis group, we were involved in several working groups with end users. So essentially, for the first time in my career, I was completely absorbed by end users. So no more requirements and specifications coming from literature analysis, but talking to the people that have to use the device. So together with colleagues that were in Scuola Sant'Anna that were hired by EUVO, having all that knowledge about upper limb exoskeletons, we met continuously for 1 year with end users, with this focus group, thinking about how devices could be done. And we came to a list of requirements, and we immediately realized, and this is something that for us was very important, because actually this is a kind of peculiarity of the technology that we have developed, that the point of having passive degrees of freedom to couple the device with the shoulder was very important. And actually, if you realized, we had a lot of attention in powered exoskeletons in passive degrees of freedom. We came together also with Ossur colleagues that developed, together with us, the garment. We came to the first edition of the Mate that reached the market on 2018 as a non-powered passive exoskeletons for relieving shoulder effort in overhead manipulation task. So this is simply, and there is nothing wrong in saying simply, okay, because sometimes young researchers want to complexify. We like to say that this is a simple device which compensates the gravity of the shoulder. I mean, acting at the shoulder level around the flexion-extension axis. So not 100%, fraction of the gravity. And the clever part of the story is in the mechanism that makes it possible to change the level of assistance so that big guys can require more assistance. Smaller guys like me maybe require less assistance. We paid a lot of attention to, as I said, reproduce with the passive degrees of chain of passive degrees of freedom the movement, the human movement, so we could align the assistance with the natural axis rotation. We wanted to improve safety and usability, or enhance usability and safety by keeping low the encumbrance of the device around the human body, because I mean these workers have to move around environment with a lot of risks of entanglement. And then the mechanism is always closed in boxes. Usually this is not typical for prototypes done in the academia. And then no encumbrance around the head, because in some cases workers have to wear helmet. Of course, we did the effort of developing different sizes of the garment, and so that we could cover more or less 90% of the male and female anthropometries in Europe. And then after a couple of years, we came with the second generation of Mate that is called the Mate XT, which is actually was delivered on December 2020, so during the pandemic. And it is one of the most performing exoskeletons on the market with only 3 kilograms of weight, okay? And is quite, I would say, quite interesting for the features that has in terms of IP protection, not intellectual property, but in instrumentation protection and certifications. I don't want to go into the details, but I want to start another story. So, with this device, we said, okay, we have reached quite nice device, quite nice tool. It works. You can, I mean, I have used also in my garden to do stuff, because I mean, I'm a lazy guy. You can do a lot of things, but it is not enough for doing money and for a market. So, and the beginning, the start was very, very slow. So we started interrogating what is missing, why this device does not sell itself alone. I mean, it's there, why people don't buy it. So developing the robot is just the starting point. Then you need to build the knowledge. So wearable robotics is not just like selling, how to say, it's not like when you sell fish, okay? So you are in the market and then you sell fish. It's quite immediate, understandable that you are I mean, that you want to buy it, you want to eat it. Here it's not exactly the case. This is a business which is science-based. You need to build a lot of knowledge because you have to communicate with a lot of different stakeholders. Workers, unions, policymakers, ergonomists, kinesiologists, occupational medical doctors, corporate management, all the decision makers in the company, insurance companies. In Italy, we have INAIL, for instance. And everybody asks for knowledge. They don't care about the price. Sometimes they care about performance, but they care about evidence. And then we came to the conclusion that the barrier to the adoption of the technology was the lack of clear evidence of effectiveness. Of course, the point is that you cannot do this alone. You need a community. So of course, we started giving our own contribution, but this is something that can be solved only at a community level. And all the actors in the field of exoskeletons for industry are now involved in these operations, in this activity, also third parties, independent players, in producing knowledge. I like to acknowledge the fact that this work that I'm citing here has been mostly done within the cost action. I think that the cost led, I mean, the action led by Jan Feneman that has paved the way for this operation of knowledge building. And the thing that you immediately realize is that there is not only the device, but there is also the environment. And the same device can bring to different evidence depending on the environment. So like in the medicine and in the medical field, also in the work and industrial field, the specificity and the precision of what you do is important. So there is not one device fitting all. And this is something that we started systematically to analyze. Okay, it seems trivial, it may be kind of obvious stuff, but for us was something that we had to understand. And actually, in this paper that you can find on wearable technologies, we talk about this roadmap towards the large-scale adoption of exoskeleton. So essentially, there has been, because in my view, the in-lab assessment era is somehow the past. Then we have the current era, which is mostly in-field assessment era, so where exoskeletons are tested in the real environment. But then there will be the large-scale adoption era when the knowledge will be more and more available, and there will be more long-term study. Okay? Because actually the questions that were raised to us were, okay, does it work? Does it work now? But what about the future? What about the long-term impact of exoskeletons for providing workers with support? Of course, this is not something that we can solve alone. As I said, it's a community effort. And without this effort, I'm sure there will be no market. Unless there will be an external factor saying, okay, from now on, everybody has to buy exoskeleton, which is our dream, but it will be a fake market. It will be a market that will be a kind of doped market, more or less similar to what is happening with electrical cars, by the way. So, in EUVO, even if it's a company, we started hiring PhDs capable of doing tests in the lab, but also doing tests in real field, in real manufacturing lines, which is a nightmare because people are not collaborative. And then I was dreaming a similar facility like the one of EUROBENCH, where you can somehow simulate the working experience. So we did a first test in the lab. I'm almost ending my talk. We did the first test in the lab. You can find all the details in the Robotics Automation magazine paper, where we tested the technology with healthy individuals, naive subjects, and showed that the device is safe to use, reduce the EMG activity, and has a good wearability. But then we started testing the device in several places, and we are systematically publishing the results. The first paper that we have published is on applied ergonomics, where the mate has been used, I cannot say which company, but has been used in an enclosure production line in mounting and dismounting tasks and hanging tasks, with extremely good result for what concerns the EMG reduction and the acceptability. In this line, in this plant, workers are using every day the mate. Similar result in a paper which is under review. We are at the second stage in applied ergonomics. In cleaning and logistics, small logistics, I must say that in the ceiling cleaning, we have achieved the best result. And I would say majority of workers that have tested the device, they don't go to work in the morning if they don't have the mate available. So, which means that where the added value of the exoskeleton is relevant, you can accept to wear 3 kilograms for 8 hours a day with no problem and no complaining. So far, this is just a list of the major environment where we have tested the technology on involving more than 100 operators, and which is the current challenge for us. We are carrying out long-term study. The ones that I showed are studies where we just tested technology for a few weeks. Now our target is testing the technology for years and see how this have an impact on the acceptability and usability, but also how this has an impact in the behavior of the subject, whether the EMG changes, there is adaptation, and possibly how this has an impact on ergonomics and ergonomics risks. I think that this year we have the first study ending, and hopefully we will publish the results, provided that we are able to convince other colleagues in the world that these are worth to be published. So, what are the lessons learned? The lessons learned are that the adoption of exoskeletons require evidence-based decisions by the stakeholders. This is true for exoskeletons for workers, but this is true for exoskeletons for medical field. It's exactly the same. So, there is no point in developing exoskeletons for medical market if we do not accept the idea that we need to provide clear evidence to the decision makers. It's just an exercise. Otherwise, this is I strongly believe in this. And we need, of course, for workers, large and longitudinal studies, but this happens the same for medical market. And in my view, for the medical market, it's even more important to be precise. The idea that you can have one exoskeleton fitting all is not applicable in my view. We have to maybe change our mindset, and instead of large trial in terms of many patients, we have to start thinking to smaller trial with homogeneous cohort of patients, and then have clear evidence of what we can produce. This is what we are doing in the industrial field, and I think that it can be a nice lesson to translate from one domain to the other. Then, of course, we should pretend in the industrial field that large companies should act like early adopters, and the same can happen in the medical market with hospitals and public institutions, considering that our target for the medical market is not only the hospital, but also providing support at home. Otherwise, this means that we didn't learn anything from the COVID. So I conclude telling that the experience matured with the mate, and that I shared with you hopefully can be inspiring or can be relevant somehow also for the medical and other industrial sector. I think that I like to say that wearable robotics is not science, it's not science fiction anymore, but is a science-based market. This is something that we should be proud of, because in many cases, in the past, roboticists were not even considered scientists. I think that this is something that we have to underline as an important fact, so which means that no science, no evidence, no market. And education cannot be neglected. I don't know what's the experience of the colleagues, the other teachers here, but we need to educate students. I remember several efforts done also by José Luis Pons with many summer schools. And in my view, we should now, because now students have a lot of, they are stressed by publish or punish. But we should try to help them in understanding that maybe it's better to publish less papers but with higher quality and clear evidence on what they do. Second conclusion is that we learned that if we want to have chances to have a large adoption of exoskeleton, we have to simplify the design. Complexity is an enemy, okay? Because already a simple design means a lot of effort, because then you have reliability. I mean, that I didn't talk about, but reliability was for us an important requirement. The mate is tested for millions and millions of cycles before breaking, which is not the case for a product that is, for a prototype that is an academic one. And then, kind of provocative question, if I really have to complexify a little bit, can passive become semi-active or semi-passive? And then a paper that we recently published in Transaction Neural System and Rehabilitation Engineering, where we transformed the mate into a spring-loaded with a small motor where you can essentially switch from one assistive curve to another by means of any algorithm that you can invent. And I think that this semi-active stuff may be also inspiring for younger researchers in the field of exoskeletons for medical market. I concluded in less than 40 minutes, and I want to thank all the guys in my lab, and I'm very happy to answer to your questions, if any. Thank you very much.
Share the microphone until a new one will appear. Okay, so thank you very much, Nicola. I'm sure there are a lot of questions. At least I have all these. Of course. Okay, but let's start with the audience if there is any. Don't be shy. So Nicola made a perturbation to our benchmarking thing because it began with the upper limb. It's very good that you did.
I did on purpose.
Eh?
I did on purpose.
So thanks, Nicola. Very nice and really interesting to see the full path from the lab to the spin-off. So I have two questions actually. The first one, a bit for curiosity to understand on this mirroring system that you go from the left to the right arm, how you deal with the mechanical stops of the, let's say, for the foot joint. Of course, if you mirror the actuator, you either to have, let's say, large rate extension without mechanical stops, will not get to. From this, how do you deal with this?
Okay, so you're right, of course. There is essentially a piece of metal that we can use to change the mechanical end stop.
Okay.
That's it. Maybe in the video, it's not immediately clear, but I can share with you some more material offline where this is more visible.
Okay.
Yeah.
Okay. And then very fast, the second one. So let's say removing the fatigue from the muscles by holding, say, the arm, and not having the mass to provide the effort to keep the arm up. Of course, relax the person, but then you may, in the long term, let's say, allow people to stand in that kind of posture for longer times, which eventually start potentially experience also stress on the circulation system, because of course you need to pump, let's say, the blood at the higher, let's say, height for a long time. Maybe have eventually this. But how do you deal with this kind of situation where, of course, the subject can still keep the arm, but maybe you stress then your heart to provide the blood on the higher height on the arm?
Okay, this is a very nice question. We have discussed this several times also with occupational medical doctors. So the point is that people should not work with uplifted arms. So the overhead task is something that should not happen. Okay, mostly because of the inherent, I would say, orthopedic risk, because of all problems and risk of syndrome at the shoulder level, but also for possible overload at the cardiac system. The point is that there are works and workstations where this is unavoidable. So the point is understanding whether by means of this device, at least you can mitigate the risk at the shoulder level for what concerns the orthopedic risk. And recently, this was discussed internally to the community of EAWS, which is a kind of scale for ergonomics risk assessment, similarly to the OCRA index. And for instance, now there is a way to compare the ergonomics risk with and without the exoskeleton in tasks of overhead manipulation. On top of that, this is not yet 100% clear. I mean, I think that more studies are needed. And that's the reason why, for instance, at least in Italy, INAIL has launched a table, a discussion table with all stakeholders to understand whether and how to recommend the use of similar devices. I don't know if this answers to your question in an extreme synthetic way. Yeah.
Hi, Nicola. Thank you very much for your very, very nice presentation and very, very impressive work. So, continuing with this comment, I work mainly in the field of medical robotics, but thinking of this application on the industry, I wonder if these exoskeletons are directed to release the effort from the worker from, let's say, repetitive work, whether or not this repetitive work should be replaced by an industrial robot, and what is going to be the role of these exoskeletons in the industrial settings, because, you know, if there is a repetitive work should be replaced by a machine, which is, you know, more precise for this kind of works.
I mean, that's a very good question. I would say that we have discussed this also with many politicians, because this is not just a matter of technology. My personal opinion is that hard works or strenuous works should not be done. So in a perfect world, everything is done by machines, and there is maybe a part of the humanity that it does not work. It just enjoy the life, and there is part of the taxes that comes from machines. I mean, this is possible. The point is what happens in the transitory phase. And in the transitory phase, there are works that machines are not able to do. And so, and there are people that do these jobs that are strenuous, like, I mean, cleaning. Cleaning, of course, you can consider to do this by means of robots, but in the meantime that robots are available, you need solutions to avoid these guys and ladies be too much tired. I want to make it clear that, but this is not only my opinion, this is the opinion of all makers of exoskeletons for workers. The ambition is not to, to offer an easy solution to owners of companies so that they say, okay, I will not invest anymore in improving the work condition because I have the exoskeleton. So there is also this aspect that has to be taken into account. So in my view, fundamentals of ergonomics say that you have to invest on the work environment and make everything you can to guarantee the best working conditions. At a certain extent, sometimes this is not resolutive, and then exoskeletons can be used and can complement the investment. But considering that the perfect world in the future has only people that enjoy the life and that don't do strenuous tasks, which is something that I am fully convinced of. So I really believe that the machines can sooner or later do the job, but not tomorrow, unfortunately.
Thank you. Very interesting talk. I was interested in the fact that you have this joint venture you mentioned, Kamau and Osho, and that you are now making systems for the two different sectors.
Yes.
So I was wondering, do you think the same technology can be used in the two sectors, or there will be some fundamental differences?
Rather than technologies, I would say that what we try to put on, like in common across domains, is the knowledge we accumulate about human body. For instance, how we do the physical human-robot interface, how we, in case of power devices, how we do the actuators and the control laws. But there is a clear difference between the sectors for what concerns the requirement and the level of, how to say, making a medical device is still more complex and requires more attention than an exoskeleton for workers. Then we may say, like other colleagues have done, like Otto Bock has recently said that an exoskeleton for workers is also a medical device, or was also Laivo, that it depends on what you claim. If you claim that you are preventing injuries, then it's a medical device, and then the evidence you need to collect are more complex than if you say, oh, I'm just reducing the workload. In this case, it's not a medical device.
The example of Cyberdyne maybe you should look at, because they tried to do the same, but they failed because the regulators...
They have the same technology in the case of Cyberdyne.
They tried to do medical and non-medical, and the regulators was not convinced.
We are following a different approach. So the technology that we are developing for the industrial market are different from... But of course, if we learn how to make a garment to attach the exoskeleton to the trunk, the same design principle will be used in devices of different kinds.
Okay,
yeah.
Great.
It's more, I would say, we try to share the know-how because the engineers are the same, of course, but the technologies are different.
Okay, great.
Yeah.
Yes, thanks, Nicola. Very nice presentation, and also nice to see that you keep moving forward with your company and your development. I was wondering about the field studies that you mentioned. Who is actually driving it in the sense of also paying for it? Is that something you have to set up as a company, or are there institutions, or is it the client, the customer that
I must say that in majority of the cases are the companies that wants to adopt the exoskeleton that say, okay, how do we adopt the exoskeletons? And then in the end of the day, they pay for the studies. Of course, we don't charge them too much because in the end of the day, we are sharing knowledge. So we just reimburse the cost of our engineers. So essentially, the business model of UVO right now is, as far as the profit and loss is in a good shape in the end of the year, we are happy because we want to grow in number of people rather than in revenues. But yeah, majority of cases are the companies to pay. And this is okay because it's a completely unexplored world for them. And in some cases, we had meeting with 10 managers of a big corporate because the introduction of the exoskeleton in the line was a problem for many different categories in the company, ranging from unions. In Italy, unions are have a very important role in the company, till the manager and the medical doctor and blah, blah, blah.
And do you then also discuss if the results can be public or?
Yes, they pay, but we have invested in making contracts in a way that they own the data, but we are free to use the data for research purposes and public them. We can publish them, provided that they essentially double check the manuscript. Oh, I mean, of course, from an ethical perspective, it's not the study that we publish have not the same impact of studies done by third parties, but we cannot wait for third-party studies. We are also interested in promoting third-party studies. We also have sponsored the third-party studies, but I think that it is a matter of, as I said, it's a matter of also of community effort. So I would like to get many other teams taking exoskeletons, not only just our exoskeleton, but all exoskeletons, and testing different conditions. There was a colleague in one of Fraunhofer Institute doing this EXA workathon, which was, in my view, a very nice initiative, but I think that facilities like the one of EUROBENCH should become, I mean, I would like to see Diego stressed by the fact that there are hundreds of projects that involve the facility, so there are tons of experimentations, and Jesus, of course. So that's the point, because this is also our advantage with respect to our US colleagues. In making studies, in particular in the industrial exoskeleton field, we are, in my view, a little bit ahead with respect to our US colleagues. Let's try for one time to keep this advantage. Okay, so maybe I'm wrong, but this is my feeling, of course.
Thanks.
Okay, now my 20 questions. Just a couple. It's about testing facility, actually. No? My first question is, as a company, would you like to be compared with competitors?
Yes, of course.
And do you think that other companies also want to be
No,
competitive?
other companies would not. But we are Italians, that's the difference.
Yeah, no. But
we don't care,
see,
even if we are not perfect.
We have only one customer. Oh,
yes.
So why?
But you can do the comparison and publish the data like this ExoWorkathon did. So they published the data looking at the entire population of exoskeletons that published the data in, average data, and then they gave back to each company data of their own device without the permission to disclose those data. So which means that I know how much I am good with respect to the competitors, but I cannot use this information for marketing purposes, which is fair. So this is a kind of compromise that our German colleagues were very clever to put together.
And why are they not giving the possibility to claim with respect to normative?
Because many companies gave the exoskeleton to them without giving the permission to make the benchmark.
But if there is a product, you can buy it and test it.
Yeah, I know that, but
no?
In principle, you can do that. In principle, I could, not me, because this would not be fair, but a third party could buy 5 exoskeletons and then make a benchmark and present the results. As I said, we are not worried about the comparison because it's something that, not all the companies that are live now will exist in the next years. So everybody has to be ready to fail or potentially fail. And only if we do this systematic benchmarking, we can keep the competition high. This is my opinion.
So the value that we are selling here is for the company that can know itself how it is with respect, say, to the, but not to claim to the general public we are.
But it's okay. You can, this is the first important step. If I have a facility where I can check how my device behaves, and then I know confidentially how much I am good or not with respect to the other, and I cannot disclose the information for the sake of, respecting my competitors, it's fine.
Okay. Now another question on testing facility. You were talking about field tests, and then you said to me,
I would
like to have in laboratory something similar to field
yes.
tests. So if you would have a testing facility with very close to real life condition, would you still need to do field tests?
But when you go to make the field test, you know exactly what to do. In our case, we struggled in making a lot of tests before finalizing the protocol. And look, if you are in a real production line and your engineers go with the exoskeletons, the EMG recorder, all the workers and the people there, they don't care about what is the objective of your work. Okay, so they are only interested in delivering stuff. It's not a game. Okay, so you are considered a distraction and a disturbance. So the protocol has to be super reliable. Okay, and in case you have a facility where you can simulate stuff, you can make your protocol strong and then you go in the field. There was no EUROBENCH for upper limb exoskeletons, and then we had to invent something. Okay.
Okay, and the last one is you talked about the generate evidence of effectiveness, no? So this turned out to have this performance indicator or metrics, no? So my question is, what would be your killer evidence, no? So your killer metrics to which to say, okay, we got it. No? We sell now.
That is not yet the killer. The one I would like to have is not yet there, which is the satisfaction of the workers that say, okay, since now I use the exoskeleton, when I go home, I feel much better. It's too early. We are still in the rising phase of the market deployment, of the deployment in the market. This KPI is not yet there. But the other ones are a good trade, good compromise, like the reduction of the EMG, the indications from the Borg scale and the usability and acceptability. But the killer one is that. the personal satisfaction of the workers. That will be the personal satisfactions of the patients in case of medical devices.
Thank you very much. So no more questions. Thank you very much, Nicola.
Thank you very much.
For staying with us. And we think we came to the end of this summit. Would like to thank you very much. I think this has been really, I would say, enriching meeting for myself at least, but I've seen that all of you enjoyed one way or another. We are, I think, a good diverse community, but we share the same goals, I would say. So we should, as I said at the beginning, keep staying together, don't lose the momentum, and find any possibility to work together in a smaller group, all together, of course, with some network that we'll try to push forward. And so any idea, any resources that you may put into this, please contact us, because we are really open. If you want to come here also in the facility to start any study together with us on one of these conditions, with one of your devices, or even to collect normative data, this would be a good way to start working together, so to continue working together. So thank you very much, and keep in touch.
And maybe one very final word. Diego, you and your team, thank you very much for arranging this very, very interesting event. And we hope to continue with this work somehow. Thank you.
Thank you. Thank you all also for your good support during all the project. Okay, so now some logistics. We will be having an internal meeting with the consortium here, so a very private and super top secret thing, so you cannot stay here, but there will be coffee break in the same floor, and you can also go then downstairs, because there will be the team still continue showing you demonstration, as you could, if you have any question about the test beds, you want to try something and stand on the movable platform or whatever, still have time to do so. And I know that many has taxis, and so have a safe trip back. So thank you.